Hello there and welcome to Physics with William, where we take complicated ideas slowly, explain them clearly and leave enough room for your thoughts to settle. Tonight we are looking at one of the most disputed ideas in modern science, the claim that our universe appears to be fine-tuned for life. Before we begin, where are you listening from tonight and what kind of place are you in? Perhaps you're in a quiet bedroom, on a late train, at a desk after a long day, or somewhere with a window open to the night. It is worth noticing that wherever you are, an enormous number of conditions had to be in place before that ordinary moment could happen. There had to be stars capable of producing heavier elements. There had to be planets, chemistry, stable matter, and enough time for living things to develop. There also had to be electricity, internet access, and a device with a battery that always seems to lose its last 10% much faster than the first 90%. If you find these slow journeys through science relaxing, interesting, or useful, for easing your mind towards sleep, you can like the video and subscribe to the channel. It helps this quiet corner of physics reach other people who enjoy big questions delivered at a reasonable volume. There is no need to solve the universe tonight. Physicists have been working on that for a while, and they have not misplaced your application if you decide to take the evening off. The central question is simple to state. Why does the universe have the particular laws, particles, forces and starting conditions that it has? We can measure many features of nature with extraordinary accuracy. We can describe how matter behaves, how stars shine, how light travels, and how the universe expands. What we often cannot do is explain why some of the basic values in those descriptions are what they are. The strength of gravity has a measured value. The electromagnetic force has a measured strength. Particles have particular masses. Empty space has properties that affect the expansion of the universe. The early universe began with a certain balance of matter, energy, smoothness, and small irregularities. Physics can use these facts to make predictions, but in many cases our current theories do not tell us why nature has those features, rather than different ones. That last sentence needs care, because nature may not have selected anything. Words such as selected, chosen, and adjusted can make it sound as though someone stood beside a control panel before the universe began. Fine-tuning does not automatically mean that. In physics, the phrase often has a more limited meaning. It describes a situation in which an outcome depends sensitively on the values of certain underlying quantities. A small change in those quantities may produce a very different result. When a theory requires an unusually precise balance to match observation, physicists may suspect that the theory is incomplete or that a deeper explanation is missing. Imagine an old radio with several tuning knobs. Turn one slightly and the station becomes less clear. Turn another and the sound disappears into static. That does not prove the radio was adjusted by a mysterious visitor. It tells you that receiving the station depends on the controls being within a suitable range. The interesting question is how those controls came to be there. Perhaps someone set them. Perhaps an automatic system searched through many frequencies. Perhaps the design of the radio makes that station easier to receive than it first appears. Perhaps the controls are not independent at all, and turning one secretly moves the others. The fine-tuned universe debate asks a similar question on a much larger scale. Some researchers argue that many features of physics fall within ranges that permit long-lived stars, complex chemistry, stable structures, planets, and eventually observers. Change certain features enough, and the universe might expand too quickly for galaxies to form. Change others, and matter might not remain stable. Stars might burn too briefly, fail to ignite, or produce very different elements. Chemistry might become too simple for anything resembling life. This can sound astonishing, and it is often presented with dramatic language. You may have heard that the odds of a life-permitting universe are impossibly small, or that changing one number by the tiniest imaginable amount would make existence impossible. Claims like these should not be accepted without checking what is being varied, what remains fixed, and how the calculation was made. Fine-tuning is not one single measurement. It is a collection of arguments about different physical quantities and those arguments do not all have the same strength. There is also an immediate problem with the word life. We know only one example of life, the life found on Earth. It uses carbon-based chemistry, liquid water, complex molecules, and a steady supply of usable energy. When physicists discuss a universe that permits life, they usually mean a universe that can support organized, information-carrying, energy-using systems at least broadly comparable to known life. That is a sensible place to start, because it is based on evidence. It is not the same as proving that every other possible form of life is impossible. A universe without carbon chemistry might still contain something we would eventually recognize as living. Or it might contain structures so unfamiliar that the word living would not fit. We do not know. This uncertainty does not make the discussion meaningless, but it does limit what can be claimed. We can ask whether different physical conditions allow stable complexity, long-lasting energy sources, and rich forms of chemistry. We should be more cautious when declaring that no observer of any possible kind could exist. Another complication is that the basic quantities of physics may not be free to vary independently. Suppose you imagine changing the strength of one force while leaving every other feature untouched. That is a useful first test, but a deeper theory might connect several quantities. If one changes, others may have to change with it. A universe that looks impossible after moving one control alone might become possible when several controls move together. This is one reason the subject remains controversial. The argument seems to invite a probability calculation, but we do not possess a box filled with universes that can be counted. We have one observable universe. We do not know the complete range of possible laws. We don't know how likely different values are. We do not even know whether some values that appear possible in our mathematical models could exist in a consistent universe. Consider a bag of numbered balls. If you draw one ball and it has the number 7, you can call the result unlikely only if you know what else was in the bag and how the draw worked. If the bag held 1,000 balls, 7 was one result among many. If every ball carried the number 7, the outcome was guaranteed. With the universe, we have seen the drawn ball, but we have not seen the bag. Supporters of fine-tuning respond that physics often reasons about possibilities before the full theory is known. Researchers compare models, explore ranges of values, and ask how robust an outcome is. If complex structures appear only in a restricted region across many plausible models, that pattern may still require explanation. It may not give a final probability, but it can reveal sensitivity. Critics reply that sensitivity alone is not enough. A value can look surprising only because we chose the wrong scale, the wrong variables, or the wrong assumptions about what could vary. Both sides have a point, which is inconvenient for anyone hoping to settle the issue before bedtime. The controversy becomes stronger when people ask what could explain the apparent tuning. One possibility is that there is no further explanation. The constants have the values they have, and that is simply a basic fact about reality. Every explanation has to stop somewhere. Perhaps this is where physics stops. Many scientists find the answer unsatisfying, but nature is not required to satisfy scientists, a policy it has enforced quite consistently. A second possibility is that a deeper theory will show that the values could not have been different. What now looks like a collection of unrelated settings may eventually follow from one underlying structure. In that case, the universe would not be balanced by coincidence. The balance would be a consequence of rules we have not yet discovered. Physics has seen similar changes before. Separate phenomena have sometimes turned out to be different expressions of the same principle. The difficulty is that a value can be necessary within a theory, while the theory itself still needs explanation. If a future theory predicts every constant exactly, we may then ask why that theory is the correct one. Still, a successful deeper theory would greatly change the fine-tuning debate. It would replace adjustable quantities with derived ones, and show that at least some of the apparent freedom was never real. A third possibility is connected to the anthropic principle. The basic idea is less grand than its name suggests. Any observer will necessarily find itself in conditions that allow observers to exist. You should not be surprised to wake up on a planet where waking up is possible. You will never open your curtains and discover that the atmosphere vanished millions of years before your birth, because in that situation there would be no you, no curtains, and probably no disagreement about whether they should be washed. This selection effect is real, but it does not automatically explain why suitable conditions exist. If there is only one universe and its properties were equally likely to take many different values, saying that we observe a life-permitting universe because we are alive can sound incomplete. It explains why we cannot observe an uninhabitable universe. It does not explain why there is a habitable one to observe. The anthropic argument becomes more powerful when combined with a multiverse. In many multiverse proposals, reality contains a vast number of regions or universes with different physical conditions. Most may be sterile. A smaller number may develop galaxies, stars, chemistry, and observers. Any observer asking about the constants will naturally be located in that smaller group. The situation would be similar to a person wondering why the planet beneath them has a solid surface. There may be many places without one, but the person could not stand there and ask the question. The multiverse is not a single theory. It appears in different forms within cosmology and interpretations of quantum mechanics. Some versions arise from attempts to understand cosmic inflation. Others emerge from theories that allow many possible states or many branches of physical outcomes. These ideas are studied seriously, but connecting them to fine-tuning creates difficult problems. Researchers must explain how different universes are produced, how their properties vary, and how probabilities should be assigned across a possibly unlimited collection. Then comes the explanation that produces the strongest reactions. Some people argue that the life-permitting character of the universe points to design. They suggest that the constants and conditions were intentionally set so that life could arise. This is why fine-tuning often escapes the physics department and appears in philosophy, theology, public debates and conversations that begin calmly and somehow end with three people talking at once. Design is controversial partly because it is difficult to test as a physical explanation. Science normally asks what a proposal predicts, what evidence could count against it, and how it compares with alternatives. A general claim that an intelligent cause wanted some form of life may be compatible with many possible observations. It may belong to philosophical or religious reasoning rather than to a predictive model of physics. That does not mean the question is forbidden. Science does not improve by banning questions that make people uncomfortable. It improves by being clear about what its methods can establish. A physicist can study how stars depend on particle properties. A cosmologist can examine how structure formation changes under different conditions. A philosopher can ask whether those findings support one explanation more than another. Problems arise when the boundaries between measurement, inference, and personal belief are hidden. There is another source of disagreement. The universe does not look uniformly friendly to life. Most of space is empty, cold, and exposed to radiation. Most planets we know are not suitable for humans. Stars explode, galaxies collide. Black holes are not noted for their hospitality. Even Earth has offered ice ages, impacts, volcanoes, disease, and weather that ignores carefully planned weekends. So, in what sense is the universe fine-tuned for life? The claim is not usually that the universe is comfortable or optimized for living creatures. It is that the underlying laws permit life somewhere. A universe can be mostly hostile while still containing rare environments where complexity develops. A large hotel may have one warm room without having been designed around the comfort of the person inside it. Critics sometimes call this carbon chauvinism, the assumption that life must resemble us. Supporters answer that carbon is not chosen merely because humans are fond of it. Carbon has chemical properties that allow it to form a remarkable variety of stable, complex structures. Water is not important because it looks pleasant beside a holiday cottage. It is an effective solvent for the chemistry used by every known organism. Stars matter because they provide long-term energy and produce many of the elements required for planets and biology. The more careful form of the argument therefore does not begin with humans. It begins with complexity. Can a universe build stable structures at more than one scale? Can it produce persistent differences in energy that systems can use? Can it support chemistry rich enough to store information, reproduce patterns, and adapt? Can it remain orderly in local regions for long enough that slow processes have time to work? Those are physical questions, though the answers are not complete. They move the debate away from the claim that the cosmos was arranged for people who enjoy tea and toward the broader question of whether any complex observers could emerge under different laws. It is also important to separate fine-tuning for life from fine-tuning inside physical theories. Physicists regularly use the language of naturalness and tuning when a model requires values to balance with suspicious precision. These concerns have guided searches for new particles and deeper symmetries. Sometimes those searches succeed. Sometimes nature refuses to cooperate and leaves an expensive machine full of very capable scientists staring at a result they did not expect. Fine-tuning for life uses related language, but it makes a larger claim. It asks not merely whether a theory looks mathematically awkward, but whether the existence of complex observers depends on narrow physical conditions. That introduces biology, chemistry, cosmology, probability, and philosophy all at once. It is difficult to isolate the variables, and even more difficult to keep everyone using the same definition. Yet the question persists because the universe does contain a striking chain of structure. Simple particles combine into atomic nuclei, electrons allow atoms to form, atoms join into molecules, gravity gathers gas into stars, stars create heavier elements and release them, planets form from the remains, chemistry becomes increasingly complex. On at least one world, some of that chemistry learned to copy itself, adapt, look at the sky, and complain about passwords. None of this proves that the underlying conditions were unlikely. It does show that the conditions are productive. Our laws do not merely permit featureless matter drifting forever. They allow layers of organization, from the very small to the very large, and they allow those layers to interact. The central dispute is about how to interpret that fact. Is it a coincidence that needs no explanation? Is it the inevitable result of a unique deeper theory? Is it a selection effect within a much larger multiverse? Is it evidence of intention? Or have we framed the entire problem badly because we do not yet understand possibility, probability, or life well enough? At present, physics does not provide a settled answer. That uncertainty is not a failure. It is an honest description of where the discussion stands. Fine-tuning is controversial because the evidence is real enough to examine, the interpretations are broad enough to conflict, and the missing information is important enough to prevent a clean verdict. For now, it helps to place the grand conclusions to one side. Before deciding what the apparent tuning means, we need to understand what is supposedly tuned. The universe does not come with visible knobs, labels, or a helpful instruction manual tucked behind the cosmic microwave background. The controls are inferred from experiments and observations. Some determine how particles interact. Some influence whether atoms remain stable. Others shape stars, galaxies, and the expansion of space itself. Once we look closely at those controls, the debate becomes less like a vague argument about whether the universe is special, and more like a series of specific questions. What happens if gravity is stronger? What changes if particles have different masses? Why does empty space affect cosmic expansion? Which conditions are truly narrow, and which may be more flexible than early estimates suggested? That is where the case for fine-tuning really begins, not with a conclusion about purpose or chance, but with the physical settings that make an organized universe possible and the surprising ways those settings depend on one another. Those settings are what physicists usually call the fundamental constants of nature. The name can make them sound like a collection of numbers printed on a label somewhere behind the universe, but they are really values that appear in our best descriptions of how matter, energy, space, and time behave. They tell us how strongly particles interact, how massive certain particles are, how quickly influences can travel, and how the large-scale universe responds to the energy contained within it. A law of physics describes a relationship. A constant helps determine the specific form that relationship takes in our universe. The law may tell us that gravity attracts matter. The relevant constant tells us how strong that attraction is. The law may describe the electric force between charged particles. Another constant sets the strength of that interaction. Without the constants, the rules would be incomplete. It would be like receiving instructions for making bread that say to combine flour, water, yeast, and salt, but do not mention how much of anything to use. You might still produce something, though it could be more useful for repairing a wall than serving with soup. These constants are not all alike. Some describe the properties of particles, such as the mass of the electron. Some describe interactions, such as the strength of electromagnetism. Some connect different parts of physics, such as the constant associated with quantum behavior. Others describe the universe on the larger scales, including the effect of empty space on cosmic expansion. Fine-tuning discussions often gather all of them under the image of cosmic dials, but that image needs to be handled carefully. A dial suggests that a value can be turned freely while everything else remains unchanged. We do not know whether nature works that way. The values may be connected by a deeper theory. What looks like 10 separate controls may turn out to be one mechanism viewed from 10 directions. Still, imagining them as dials is useful because it lets researchers ask a clear question. If this value were different, while the rest of our physical description stayed roughly the same, what would happen? One of the best-known constants is the speed of light in empty space. It is not only the speed at which light travels, it is also the maximum speed at which information and causal influence can move through ordinary space-time. It helps connect space and time, energy and mass, electricity and magnetism. In our present system of measurement, its numerical value is fixed exactly because the unit of length is defined using it. That does not make the underlying feature arbitrary. It means we chose our measuring system around a property of nature that experiments showed to be extremely stable. This raises a small but important issue. The numerical value of a constant can depend on the units we use. A distance looks different when measured in miles rather than kilometers, even though the road has not changed. For fine-tuning, physicists therefore pay special attention to quantities that have no units. These are pure ratios or combinations of constants. Their values do not change because someone replaced meters with feet, or seconds with an especially inconvenient historical unit. The fine structure constant is one such quantity. It describes the effective strength of electromagnetic interaction between charged particles. It influences the structure of atoms, the way electrons occupy energy levels, and the details of how atoms absorb and emit light. Its name comes from the fine structure seen in atomic spectra, where lines that first appear simple split into closely spaced patterns when examined carefully. Electromagnetism is central to the ordinary world. It holds electrons around atomic nuclei. It allows atoms to bond into molecules. It is responsible for most of the forces you notice when touching solid objects. The table supporting a cup is not holding it up because the pieces of matter are tiny blocks pressed directly together. The charged particles in the atoms resist being pushed into the same states. The result feels solid, which is fortunate because breakfast becomes complicated when tables behave more like suggestions. If electromagnetic interaction were different, atomic structure would change. Chemical bonds could be weaker or stronger. The sizes of atoms and the energies involved in reactions would shift. That does not mean that the slightest change would erase all chemistry. Nature often has ranges rather than single, permitted points. The serious question is how wide those ranges are and whether other constants could change at the same time in ways that preserve complexity. Gravity occupies the opposite end of our everyday intuition. It is the weakest of the familiar fundamental interactions when individual particles are compared, yet it dominates planets, stars, galaxies, and the evolution of the universe. It wins on large scales because gravity is always attractive for ordinary matter and because mass adds together. Positive and negative electric charges can cancel, but there is no familiar negative mass available to cancel the gravitational pull of a star. The weakness of gravity is one of the features often discussed in fine-tuning arguments. If gravity were substantially stronger relative to the other interactions, stars could be smaller, hotter, denser, and shorter lived. If it were much weaker, gathering matter into stars and galaxies could become more difficult or require different conditions. The exact consequences depend on which other properties are held fixed, and models can sometimes find stable stars across wider ranges than simple arguments suggest. Even so, gravity clearly helps determine the size, temperature, pressure, and lifetime of stars. Long-lived stars matter because complex processes need time. A star is not simply a lamp suspended above a planet. It is a controlled gravitational system in which inward compression is balanced by outward pressure. Nuclear reactions in the core provide energy, while gravity keeps the fuel confined. Change the balance, and the star may burn differently. It may use its fuel quickly, struggle to ignite, collapse, or settle into a form unlike the stars we know. Inside the atomic nucleus, the strong interaction does another essential job. Protons have positive electric charge and repel one another, yet many of them remain packed together in nuclei. The strong interaction, acting through the underlying behavior of quarks and gluons and through the effective force between protons and neutrons, provides the binding that makes larger nuclei possible. Its strength affects which nuclei are stable. If nuclear binding changed, the periodic table could look very different. Some elements might fail to exist, others might become more stable. The processes inside stars would follow new routes. A universe with altered nuclear physics would not simply be our universe, with different labels on the chemistry set. It could have different fuel, different stellar lifetimes, and different raw materials for planets. There is a common simplified claim that a tiny increase in the strong interaction would bind two protons together and cause all hydrogen to disappear early in cosmic history, while a tiny decrease would prevent heavier elements from forming. The real situation is more complicated. Nuclear reactions depend on several quantities, including particle masses, electromagnetic repulsion, reaction rates, and the conditions inside stars. Researchers do find important sensitivities, but the permitted regions can expand when several parameters are varied together. The lesson is not that every dial has one exact safe position. It is that nuclear stability depends on a network of balances. Carbon provides a famous example. In evolved stars, carbon can form through a process in which helium nuclei combine in stages. The production is helped by a particular excited state of the carbon nucleus, often called the Hoyle state. Its properties make carbon production far more effective under stellar conditions than it would otherwise be. Fred Hoyle argued that such a state should exist before it was experimentally confirmed, reasoning from the fact that carbon is abundant and that known stellar processes needed a way to make it. This story is sometimes presented as decisive proof of extreme fine-tuning. Modern studies give a more careful picture. Shifting the relevant nuclear properties can change the amounts of carbon and oxygen made by stars, sometimes strongly. More detailed stellar models have also found that useful production may continue across a broader range than older estimates suggested. The case remains important, but it is not well described by saying that moving one invisible knob by the smallest amount destroys every carbon atom. The masses of elementary particles also function like settings. The electron is much lighter than the proton. That difference helps determine atomic size, chemical behavior, and the way matter responds to energy. The masses of the light quarks contribute to the properties of protons, neutrons, and atomic nuclei. The neutron is slightly heavier than the proton in our universe, a small difference with major consequences. Because the neutron is heavier, a free neutron can decay into lighter products. Inside a stable nucleus, the balance can be different because nuclear binding matters. If the neutron and proton masses were arranged differently, hydrogen stability and nuclear reactions could change. A universe in which the proton readily transformed into a neutron would have difficulty retaining ordinary hydrogen. A universe with a larger mass difference could face other problems when building nuclei. Once again, the outcome depends on several connected values rather than one isolated setting. The weak interaction is less visible in daily life, though it plays an important part in radioactive decay and in reactions involving neutrinos. It helps govern processes that allow stars to begin converting hydrogen into helium. The slowness of certain weak interaction processes contributes to the long lifetime of stars like the Sun. A reaction that is difficult to start can be very useful when you want a star to release energy steadily for billions of years rather than finish the job before the surrounding planets have properly cooled. Changing the weak interaction would alter stellar burning, the behavior of unstable particles, and the production of elements in the early universe and in stellar explosions. Some universes with different weak physics might still produce stars and chemistry through alternative routes. Researchers have even examined hypothetical universes with no weak interaction as we know it, and found that some forms of complexity may remain possible if other conditions are adjusted. This is a useful warning against claims that every familiar ingredient is individually indispensable. The purpose of varying constants is not to create a cosmic version of removing one ingredient from a recipe while refusing to change anything else. It is to learn which features are robust, which are fragile, and which can be replaced. Life does not require that every event in our cosmic history happen in exactly the same way. It requires some route to stable matter, usable energy, rich chemistry, and persistent environments. There may be more than one route. A particularly difficult setting is associated with the energy of empty space. Empty space in modern physics is not simply an absence of everything. Quantum fields remain present, and the vacuum can have physical effects. On cosmic scales, the observed behavior linked to dark energy causes the expansion of the universe to accelerate. The quantity used to describe this effect is often called the cosmological constant, though not every model of dark energy requires it to be truly constant. If the repulsive effect associated with empty space were much larger and positive, matter could be driven apart so rapidly that galaxies would struggle to form, gas would not gather into stars in the usual way, and the large structures needed for planets and chemistry might never develop. If the value were sufficiently negative, the universe could stop expanding and collapse before complex structures had enough time to appear. The cosmological constant is especially troubling because basic estimates from quantum field theory and the observed cosmic value do not fit together naturally. Explaining the mismatch is one of the major unsolved problems in theoretical physics. Fine-tuning enters here in two different forms. There is a theoretical tuning problem involving why vacuum energy is so small compared with simple expectations, and there is a life-related question involving why it lies in a range that allows gravitational structures to develop. These are related but not identical. Solving the mathematical problem might reveal a mechanism that sets the value. Explaining why observers measure the value they do may involve selection effects, a deeper law, or something else. It is possible for one explanation to address both questions, but that has not been established. Not every cosmic dial is a constant in the strict sense. The initial conditions of the universe also matter. Early space was extremely hot and dense, but it was also remarkably smooth on large scales, with small variations in density. Those variations later grew under gravity and became the seeds of galaxies and clusters. If the early universe had been perfectly smooth, there would have been no denser regions to begin forming structure. If the irregularities had been much larger, matter could have collapsed too quickly into dense objects, possibly producing a universe dominated by violent environments rather than stable galaxies like our own. the starting level of disorder, the amount of matter, the balance between ordinary matter and dark matter, and the initial expansion all influence what comes later. The low entropy of the early universe is another source of deep questions. The universe began in a state that allowed an enormous increase in entropy over time. That difference between an ordered past and a less ordered future gives physical processes their direction, and creates opportunities for stars, planets, weather, metabolism, and all the other systems that use energy moving from concentrated forms to more spread out forms. Why the beginning had such special properties remains unclear. Dark matter adds another setting to the list. It does not interact with light in the ordinary way, but its gravity helps build the framework in which galaxies form. Regions of dark matter began gathering material, allowing ordinary gas to fall inward and eventually form stars. A different amount or different behavior of dark matter would change the timing, size, and distribution of galaxies. Whether life requires dark matter exactly as it appears in our universe is uncertain, but cosmic structure certainly depends on the gravitational ingredients available. Even the number of large spatial dimensions has entered fine-tuning discussions. We experience 3 directions of space in which objects can move. Mathematical models can imagine other numbers, but forces and stable orbits behave differently in those settings. Chemistry, planetary systems, and complex structures may face serious difficulties when the number of dimensions changes. This is not a dial that can be adjusted in a laboratory, and it may not be a free choice in a deeper theory, but it shows how broad the question can become. At this point, the control panel is beginning to look crowded. Gravity, electromagnetism, nuclear forces, particle masses, vacuum energy, dark matter, initial density variations, entropy, and dimensionality all seem to contribute. It would be easy to look at the list and conclude that everything had to be set independently, with impossible precision. That conclusion moves too quickly. Some quantities may follow from others. Some may vary only within restricted ranges allowed by mathematical consistency. Some apparent sensitivities may disappear when stars, chemistry, or life are modelled more flexibly. The universe does not have to reproduce humans, Earth, or the Sun. It needs only some environment in which organised systems can persist and develop. There is another subtlety. The strengths of interactions are not always fixed in the simple way the word constant suggests. In quantum field theory, the effective strength of an interaction can depend on the energy scale at which it is measured. Physicists describe these values as running with energy. The familiar low-energy value of electromagnetism is not quite the same as its effective value in extremely energetic particle collisions. This does not mean the laws change unpredictably from one afternoon to the next. The change follows precise theoretical rules. It does mean that the dial metaphor hides some machinery. A setting observed at low energy may be the result of how a deeper theory behaves across many scales. Values that look unrelated in ordinary conditions might move toward a common pattern at higher energies. That possibility motivates attempts at unification. Physicists would like to understand whether the strong, weak, and electromagnetic interactions emerge from a more basic framework. They would also like to include gravity in a consistent quantum description. A successful theory might explain particle families, masses, interaction strengths, and perhaps the properties of space-time itself. So far, no accepted theory derives every observed constant from a single unavoidable principle. Existing theories contain measured inputs. Researchers use experiments to determine those values and then calculate what follows. This method is extraordinarily successful. It can predict the behavior of particles and materials with remarkable precision. Its success makes the unanswered question sharper rather than weaker. We know very well what the constants do. We do not know why they have their particular values. There may also be no meaningful answer to why. The constants could be basic facts. Asking why gravity has its strength might be like asking why a particular logical truth is true. On the other hand, history advises some patience before declaring a feature fundamental. Temperature once seemed like a basic property of matter before it was understood through the motion of particles. The diversity of chemical elements became clearer through atomic structure. Separate electric and magnetic effects were joined into one theory. Fine tuning arguments live in the gap between those possibilities. If the constants are independent and could have taken a wide range of values, the life-permitting region may be unusual. If a deeper law fixes them, the appearance of tuning may fade. If many regions of reality realize different values, selection effects may become important. If our idea of possible life is too narrow, the permitted range may be larger. Each answer changes what the control panel means. The first task is therefore descriptive rather than philosophical. We identify the settings, calculate their consequences, and test which combinations produce stable structure. This work is difficult because changing a basic constant affects many systems at once. Alter electromagnetism, and you change atoms, chemistry, nuclear reaction barriers, stellar interiors, and the transparency of matter. Alter particle masses and you change nuclear stability, reaction thresholds, and the behavior of the early universe. Computer models can explore some of these changes, but every model makes assumptions. A simulation cannot search every logically possible law of nature. It usually varies selected parameters within a familiar mathematical framework. The result tells us about that framework, not about every universe that could ever exist. Even with those limits, the exercise is revealing. Some changes appear surprisingly tolerable. Stars can exist under a wider variety of conditions than a simple picture might suggest. Chemistry can adjust in ways that preserve useful complexity. Other changes cause serious problems quickly. Stable nuclei disappear, structure formation fails, or cosmic expansion ends before long-lived systems can emerge. The cosmic dials are therefore neither a row of single exact settings nor a meaningless metaphor. They are a way of organizing a real scientific investigation into the dependence of structure on basic physics. The investigation does not yet tell us whether the values were chosen, selected, required, or accidental. It tells us which parts of reality depend on them and where our understanding remains incomplete. To see why the debate becomes so intense, we have to do more than name the controls. We have to begin turning them in thought, one at a time and then in combinations, and follow the consequences from the first particles to atoms, stars, galaxies, and any environment capable of supporting complex chemistry. That is where general statements about a special universe become concrete, because each proposed change leaves a different universe behind. That different universe may still contain matter, stars, and chemistry, or it may become almost empty before anything complicated has a chance to form. The result depends on which number changes, how far it moves, and whether the other numbers are allowed to move with it. This is where the fine-tuning discussion becomes more useful, because instead of asking whether the universe looks special in a general sense, we can ask what actually happens when its physical properties are altered. The first thing to understand is that there is no laboratory where a physicist can turn down gravity, wait for a replacement universe to develop, and return after lunch to inspect the galaxies. These changes are explored through mathematical models and computer simulations. Researchers begin with laws that resemble the ones we know, adjust selected values, and calculate the consequences. The exercise cannot cover every possible kind of reality, but it can show how familiar structures depend on familiar physics. Gravity is an obvious place to begin because it organizes the universe on large scales. It gathers gas into galaxies, compresses material inside stars, holds planets in orbit, and keeps your socks on the floor rather than allowing them to drift through the room. Gravity is extremely weak between individual particles, but it becomes important when enormous amounts of matter collect in one place. Suppose gravity was stronger while the properties of particles and nuclear reactions remained similar. Clouds of gas would collapse more easily. Stars could form from smaller amounts of material because less mass would be needed to create sufficient pressure and temperature at their centers. Those stars would tend to be denser and would process their fuel under more intense conditions. A stronger pull does not simply make a star brighter in the same way that turning up a lamp makes a room brighter. A star constantly adjusts to the competition between gravity pushing inward and pressure pushing outward. Stronger gravity squeezes the core more firmly. The core becomes hotter, nuclear reactions proceed more rapidly, and the star can use its fuel faster. Many stars in such a universe might have shorter lives. This would matter for any slow process taking place on nearby planets. Life on Earth required a long period of chemical and biological development before organisms became complex. Another form of life might develop faster, but complicated systems generally need time to assemble, reproduce, adapt, and recover from disasters. A universe filled mainly with short-lived stars would offer fewer stable environments for those processes. Stronger gravity could also make dense objects more common. Large stars might collapse more readily. Planetary surfaces could have stronger gravitational fields depending on how planets formed and how much matter they contained. Mountains would be lower because rock would collapse under its own weight more easily. Atmospheres could be held more tightly, although high pressure is not automatically useful. A planet with an atmosphere thick enough to crush complex structures would be very good at keeping its air and less impressive at hosting visitors. Now reduce gravity instead. Gas would be harder to compress, and larger clouds might be needed before stars could ignite. Stars could become larger and cooler in some ranges of the altered physics. Their internal conditions would change, as would their lifetimes and brightness. If gravity became too weak relative to other processes, matter might struggle to gather into stars at all, especially if cosmic expansion continued pulling regions apart. The important point is that the permitted range is not necessarily tiny. Studies of hypothetical stars have found that sustained nuclear burning can occur across a substantial region of possible gravitational and electromagnetic strengths. Stars do not vanish the instant gravity moves away from its observed value. They change their sizes, temperatures, and lifetimes, and only after larger shifts do familiar stellar solutions become unavailable. This already complicates the simplest version of the fine-tuning story. A person might imagine a single mark on a dial with disaster immediately on either side. Actual models often reveal a broad area containing many types of stars. That does not eliminate fine-tuning, because not every star is useful for complex chemistry or habitable planets. It does show that the question cannot be answered by saying that stars require one exact strength of gravity. Electromagnetism creates a different set of consequences. It controls the attraction between electrons and atomic nuclei, the repulsion between particles with the same electric charge, and the bonds that join atoms into molecules. Most ordinary material behavior comes from electromagnetic interaction. Friction, chemical reactions, light absorption, the stiffness of a chair, and the mild irritation caused by static electricity are all connected to it. Make electromagnetism stronger, and electrons would be held more tightly around nuclei. Atoms would become smaller in characteristic size, and the energies involved in atomic transitions and chemical bonds would increase. Chemical reactions could release and require different amounts of energy. The temperatures at which substances melt, boil, or react would shift. Stronger electric repulsion between positively charged nuclei would also make nuclear fusion more difficult. Atomic nuclei must approach very closely before the strong nuclear interaction can bind them or allow a reaction to proceed. Their electric charges resist that approach. Stars would need hotter and denser cores to overcome the stronger barrier. Gravity might still provide those conditions if it were also stronger, which is an example of one change compensating for another. If electromagnetism became weaker, electrons would be held less tightly. Atoms would be larger, chemical bonds would generally become less energetic, and matter would respond differently to heat and radiation. Weaker electric repulsion would make it easier for nuclei to approach during fusion. Stars might ignite under less extreme conditions. Yet if the interaction weakened too far, the stable organization of electrons around nuclei and the richness of chemistry could be reduced. These statements describe tendencies, not exact boundaries. Chemistry contains many roots and combinations. A change that weakens one bond may strengthen the relative importance of another process. New stable molecules might exist even if familiar molecules did not. There would be no oak trees, coffee, or late-night videos, but the absence of familiar objects is not the same as the absence of every possible organised system. The strong nuclear interaction is often presented as a much more sensitive control. It helps hold protons and neutrons together inside atomic nuclei. Without adequate nuclear binding, the universe could contain little more than hydrogen. With different binding, it could produce a very different collection of elements. Reduce the effective nuclear attraction enough, and deuterium may become unstable. Deuterium is a form of hydrogen whose nucleus contains one proton and one neutron. It plays an important part in the chain of reactions that powers ordinary stars. If it could not remain bound, the usual route from hydrogen to helium would be interrupted. That sounds like the end of stars, but the outcome is not quite so simple. A star is a patient and adaptable physical system, although it would probably object to being described that way. If the easiest reaction route is unavailable, other routes may operate at higher temperatures or through different intermediate steps. Some models find that stars could still release energy even without stable deuterium, though their structure and fuel cycles would change. Move the nuclear attraction in the opposite direction, and two protons might form a stable bound state. This hypothetical object is often called a diproton. A common claim says that stable diprotons would allow hydrogen to fuse so quickly that stars would burn out almost immediately. Under that picture, the night sky would enjoy a brief and energetic youth followed by a very long retirement. More detailed studies suggest that stars can regulate themselves. If nuclear reactions become easier, a star does not necessarily continue burning at the same temperature and density. It can expand and cool. The lower core temperature slows the reactions until energy production again balances the star's needs. Stable diprotons would produce very different stellar behaviour, but they would not automatically cause every star to explode or consume all its fuel in moments. This ability to adjust is one of the most important lessons in the subject. Stars are not fixed containers in which reactions proceed at whatever rate the particles prefer. Their pressure, temperature and size respond to energy production. When reactions accelerate, the star expands. When reactions slow, gravity compresses the core. This feedback allows stable burning across conditions that may initially look impossible. The same caution applies to carbon. Carbon is essential to known biology because one carbon atom can form several strong bonds and participate in an enormous variety of molecules. Much of the carbon in the universe is produced inside stars when helium nuclei combine. The process depends strongly on the energy levels of carbon and on the temperatures inside stellar cores. Altering the nuclear interaction changes those energy levels. Some calculations show that relatively small changes can greatly reduce the simultaneous production of carbon and oxygen in familiar stars. A universe might produce plenty of carbon but little oxygen, or plenty of oxygen but little carbon. Since known life uses both, this looks like a serious restriction. Later work has shown that stellar adjustment and alternative conditions can preserve useful production across a wider range than the most dramatic claims imply. Stars with different masses and temperatures may compensate for altered reaction rates. The available amount of carbon or oxygen can still fall sharply, but the boundary between abundance and total absence is not always as narrow as a single calculation suggests. There is also no agreed minimum amount of carbon required for life. Earth does not need every carbon atom in the universe. It needs enough carbon in suitable locations. A large reduction in total production might still leave carbon-rich regions. On the other hand, an extremely low abundance could make suitable planets rare enough that the chance of life becomes very small. This is difficult to estimate when our sample of inhabited planets contains exactly one member and refuses to provide useful statistics. Particle masses create another chain of changes. The proton and neutron have nearly the same mass, but the neutron is slightly heavier. That small difference affects radioactive decay, the survival of hydrogen, and the kinds of nuclei that remain stable. If the neutron were sufficiently lighter than the proton, Ordinary hydrogen could become unstable. A proton might convert into a neutron through available processes, removing the simplest and most abundant atomic nucleus. Water as we know it would not exist because water requires hydrogen. Ordinary stars would lose their main fuel. Chemistry could still use other nuclei, but the starting material of our universe would be transformed. If the neutron became much heavier, neutrons inside nuclei would be more difficult to retain. Many elements could become unstable. The path from simple nuclei to heavier ones would narrow, and the periodic table could lose much of its present variety. Nuclear reactions during the early universe and inside stars would produce different mixtures. The electron mass matters as well. A heavier electron would orbit closer to the nucleus in the quantum description of atoms, and would change atomic energy scales. Chemical bonds and reaction temperatures would shift. If electrons became too massive relative to nuclei, the distinction between electronic and nuclear motion that makes ordinary chemistry manageable would weaken. If they became much lighter, atoms would grow larger and bonds would become less energetic. One altered mass can also affect whether certain decays are possible. A process can occur only when the starting particles have enough mass energy to produce the final particles. Small changes can open one route and close another. Matter that is stable in our universe might decay in another, while particles that quickly disappear here might remain. The weak interaction provides a good demonstration of how misleading isolated changes can be. It is involved in forms of radioactive decay, neutrino behavior, the early production of elements, and the slow beginning of hydrogen fusion in stars like the Sun. It might seem obvious that removing the weak interaction would make a habitable universe impossible. Researchers have constructed models of a universe without the weak interaction, while adjusting other physical and cosmological conditions. In those models, the early universe can still produce a useful mixture of elements. Stars can form, burn for billions of years, create heavier nuclei, and disperse those materials. The stars would not work exactly like ours, but the main requirements for complex chemistry could remain. This does not prove that a weakless universe is likely. It proves that the weak interaction is not independently required in the simple way people sometimes assume. Several changes made together can preserve structure. Whether those coordinated values are natural, probable, or permitted by a deeper theory is another question. Cosmic expansion introduces effects that cannot be repaired as easily. Empty space appears to contain a small amount of energy that accelerates the expansion of the universe. If that effect were much stronger and positive, distant regions would separate more rapidly. Small variations in matter density would have less time to grow. Gas might never gather into galaxies, and without galaxies there would be few ordinary sites for long-lived stars. A somewhat larger value does not instantly prevent all structure. Dense regions can collapse earlier, and smaller galaxies may still form. The boundary depends on the amount of matter, the initial density variations, and the assumptions used to connect galaxies with observers. Even so, make the repulsive effect large enough and expansion wins before matter can organize itself. A sufficiently large negative value would create the opposite problem. Instead of accelerating forever, the universe could reach a maximum size and collapse. Stars and planets might begin to form, but the available time could be too short for long biological development. A universe that ends quickly is not necessarily empty. It is simply working to a schedule that complex organisms may find unreasonable. The initial variations in density provide another control. The early universe was very smooth, but not perfectly smooth. Some regions contained slightly more matter than others. Gravity amplified these differences, allowing the denser regions to gather more material and eventually form galaxies. If the variations were much smaller, structure would form later, or perhaps not at all before accelerated expansion separated the matter. The universe could remain a thin and nearly uniform gas. It might contain particles and radiation for an immense period, without producing many concentrated energy sources. If the variations were much larger, matter would collapse earlier into dense structures. That could produce more black holes, more violent stellar environments, and frequent close encounters between stars. Planets might have difficulty maintaining stable orbits in crowded regions, yet stronger variations might also allow galaxies to form even when the energy of empty space was larger. One apparently harmful change can offset another. The amount of ordinary matter compared with radiation affects the timing of structure formation and the production of elements. The amount and behaviour of dark matter influence how quickly galaxies assemble. Changing either one would alter the sizes of galaxies, the abundance of stars, and the distribution of heavy elements. Some combinations would leave too little matter for useful structures. Others might create dense universes where destructive encounters are common. Each case leads back to the same methodological problem. What should remain fixed while one number changes? Holding everything else constant is easy to understand and useful for identifying sensitivity. It may also create universes that no deeper theory would ever produce. Allowing every value to change can reveal more viable possibilities, but it becomes difficult to decide which combinations deserve equal consideration. There is no accepted probability distribution for fundamental constants. We do not know whether a value twice as large is as plausible as 1/2 as large. We do not know whether the constants can vary continuously, take only certain values, or have no freedom at all. Without that information, mapping a life-permitting region does not tell us the odds of landing inside it. Imagine drawing a small habitable area on a map without knowing how travellers enter the country. If arrivals are spread evenly across the map, the size of the area matters. If every road leads directly to it, its small size is irrelevant. If most of the map cannot physically be reached, measuring the entire area gives the wrong impression. Fine-tuning calculations often describe the map more confidently than they describe the roads. What happens when the numbers change is therefore neither universal destruction nor guaranteed survival. Some changes remove familiar structures quickly. Others produce stars and chemistry that remain surprisingly workable. Coordinated changes can rescue universes that fail when one setting moves alone. There may also be forms of complexity outside the range of our models, based on physical processes we have not considered. The strongest fine-tuning cases tend to involve requirements that are difficult to replace. Matter must form stable structures. There must be persistent sources of usable energy. The universe must last long enough for organization to develop. Some mechanism must create differences between concentrated and dispersed energy, because a universe already at complete equilibrium cannot power metabolism, computation, or sustained change. A universe does not need the exact sun, the exact earth, or the exact history that produced human beings. It does need enough structure to avoid being either completely featureless or immediately destructive. Between those outcomes lies a range of possibilities. The width of that range is the real subject of dispute. Finding stars somewhere in a model is only the beginning. Those stars must produce useful energy for long periods. They must create or coexist with elements capable of forming complicated molecules. Matter must collect into environments where those molecules can interact without being constantly destroyed. The next step is to follow the altered numbers into those environments and ask how narrow the route really is from basic forces to stars, from stars to chemistry, and from chemistry to anything that might reasonably be called alive. That route begins with stars, because chemistry needs ingredients, and most of those ingredients did not exist in useful amounts at the beginning of the universe. The early universe produced mostly hydrogen and helium, along with small traces of a few other light elements. That was enough to create the first generation of stars, but it was not enough to create rocks, oceans, cells, or anything likely to worry about whether it had remembered to lock the front door. The first stars formed when gravity pulled enormous clouds of hydrogen and helium together. As a cloud contracted, its centre became hotter and denser. Eventually, the conditions became extreme enough for nuclear reactions to begin. Hydrogen nuclei combined through a sequence of processes, releasing energy and producing helium. The outward pressure created by that energy resisted the inward pull of gravity, allowing the star to remain stable. This balance is one of the first major requirements on the path toward life. A star must be able to form, begin nuclear burning, and remain active for a useful length of time. If gravity overwhelms the pressure too quickly, the star collapses or burns through its fuel rapidly. If the reactions cannot begin, the cloud may never become a true star. If the energy escapes in the wrong way, the object may fail to maintain a stable interior. Our universe contains a wide range of stars. Some are small, cool, and long-lived. Others are large, hot, and short-lived. This variety is important because different stars perform different jobs. Smaller stars can provide steady energy for very long periods. Larger stars manufacture heavier elements and spread them through space when they lose material or explode. A universe containing only small stars might have long-lasting energy sources, but struggle to make enough heavy elements. A universe containing only massive stars might produce many elements, but provide few calm environments where planets could remain undisturbed for billions of years. The path to life may therefore benefit from a mixture of stellar types rather than one perfect kind of star. The rate at which stars burn depends on gravity, particle masses, and the strengths of the nuclear and electromagnetic interactions. These properties determine how strongly the stellar core is compressed, how difficult it is for nuclei to approach one another, and how much energy is released when they combine. A useful star needs reactions that are possible, but not too easy. The Sun illustrates this balance. Its core contains an enormous amount of hydrogen at very high temperature and pressure, yet individual hydrogen nuclei still have difficulty beginning the process that eventually turns them into helium. The first important step is slow because it depends on the weak interaction. That slowness is one reason the Sun can shine steadily for billions of years. If the process were much faster, the Sun would not necessarily explode immediately, because stars can adjust their size and temperature. Even so, a major change in the reaction rate would alter the structure and lifetime of the star. A faster burning star would need to expand and cool to maintain balance. A slower process would require greater compression and a hotter core. The existence of self-regulating stars broadens the range of possible universes. It means the physical conditions do not need to produce exactly the reaction rates found in the Sun. Stars can respond to changes. They can become larger or smaller, hotter or cooler, brighter or dimmer. This flexibility is one reason careful studies often find more habitable possibilities than the most dramatic fine-tuning claims suggest. Flexibility has limits. A star still needs a source of energy that can resist gravity for a long time. It must release enough energy to remain stable without consuming its fuel too quickly. It must also send energy into its surroundings in a form that planets or other structures can use. Once a star begins producing helium, further nuclear reactions can create heavier elements. The details depend on the mass and age of the star. When hydrogen fuel becomes scarce in the core, the star changes its structure. In sufficiently massive stars, the core becomes hot enough for helium nuclei to combine and form carbon. Later stages can produce oxygen and other elements. Carbon is often central to the fine-tuning discussion because it is central to known life. A carbon atom can form several chemical bonds, including bonds with other carbon atoms. This allows carbon to create chains, rings, branching structures, and large molecules with varied shapes and functions. Proteins, genetic material, fats, sugars, and many other biological substances rely on this flexibility. Carbon is not the only element capable of forming complicated compounds. Silicon is frequently mentioned as an alternative because it belongs to the same broad family of elements and can also form several bonds. Yet silicon chemistry behaves differently. Silicon bonds with oxygen very readily, often producing stable minerals rather than the flexible range of molecules used by life on Earth. Many silicon compounds are less suitable in liquid water, and long silicon chains are generally less versatile under familiar planetary conditions. This does not prove that silicon-based life is impossible. It shows that carbon has a particularly useful combination of stability and adaptability. Its bonds are strong enough to maintain complex structures, but can still be rearranged through chemical reactions. A molecule that never changes cannot support much metabolism, while a molecule that falls apart instantly cannot store information. Biological chemistry needs structures that are stable without becoming permanently unresponsive. The production of carbon inside stars depends on nuclear properties that happen to support an efficient route. Helium nuclei first combine into an unstable intermediate state. A further helium nucleus can then join before that state breaks apart, producing carbon. A particular energy state within the carbon nucleus greatly increases the effectiveness of this process under stellar conditions. If the relevant nuclear properties changed, carbon production could decrease. The same changes could affect the production of oxygen, which forms when carbon captures another helium nucleus. Carbon and oxygen therefore compete within stars. Conditions that encourage one process may reduce the amount of material available for the other. Known life uses both elements extensively. Carbon provides the framework for complex organic molecules. Oxygen appears in water and in many biological compounds. It also supports the energy-releasing metabolism used by complex organisms on Earth, although the earliest life did not depend on free oxygen in the atmosphere. A universe does not need equal amounts of carbon and oxygen. It needs enough of the useful elements to create suitable environments. The total abundance can be lower than in our universe, while still allowing some planets to receive adequate material. Fine-tuning claims become less certain when they move from asking whether an element exists to asking how much of it life requires. The same issue applies to many other elements. Nitrogen is important in proteins and genetic material. Phosphorus contributes to genetic molecules, cell membranes, and the transfer of energy within cells. Sulfur appears in proteins and metabolism. Metals such as iron, magnesium, zinc, and copper help biological reactions proceed. These elements are created through different nuclear processes. Some form inside ordinary stars. Others are produced in the final stages of massive stars, in stellar explosions or during collisions involving dense stellar remnants. The details remain an active area of research, but the general conclusion is clear. Life needs a universe capable of producing a range of nuclei, not merely hydrogen and helium. Producing the elements is not enough. They must leave the stars and enter new clouds of gas and dust. Massive stars help by ejecting material through winds and explosive deaths. Smaller stars can also release enriched material during later stages of their evolution. This recycled matter becomes part of new stars, planets, moons, asteroids, and smaller objects. The first generation of stars formed from almost pure hydrogen and helium. Rocky planets like Earth could not have formed around those earlier stars because the necessary solid materials were not yet available. Several cycles of stellar formation and death were needed before space contained significant amounts of carbon, oxygen, silicon, iron, and other heavy elements. This places a minimum timescale on the emergence of familiar life. The universe first had to form stars, allow them to manufacture elements, spread those elements, and form later generations of planetary systems. Life could not begin immediately after the universe cooled enough for atoms to exist. The kitchen had opened, but most of the ingredients had not arrived. Planet formation adds another set of conditions. Around a young star, a rotating disk of gas and dust can develop. Small particles collide and sometimes stick together. Larger bodies gradually form, although the process is not simple or gentle. Growing planets collide, break apart, merge, migrate through the disk, and influence one another through gravity. A suitable planet does not necessarily need to resemble Earth in every detail. It may be larger or smaller. It may orbit a different type of star. It may have oceans beneath ice, chemistry in clouds, or habitable regions far below the surface. What it needs is an environment where complex molecules can form, remain present, and interact over long periods. Temperature matters because chemical reactions depend on it. At very low temperatures, many reactions proceed too slowly. At very high temperatures, complex molecules break apart. Between those extremes, matter can maintain structure while still undergoing useful change. Liquid solvents are valuable because they allow molecules to move, meet, react, and separate. Water is especially useful. It remains liquid across a significant range of temperatures under suitable pressure. It dissolves many substances, supports varied chemical reactions, and participates directly in biological processes. Water also has unusual physical properties. Solid water is less dense than liquid water, so ice floats. This allows a layer of ice to form at the surface of a lake while liquid water remains beneath it. If ice sank, bodies of water could freeze from the bottom upward, changing the stability of aquatic environments. Water can absorb a large amount of heat without changing temperature rapidly. This helps moderate climates and reduces sudden temperature changes inside organisms. It also transports substances effectively. These properties make water a strong candidate for supporting life, although other liquids have been considered in colder or chemically different environments. For water to remain liquid, pressure and temperature must fall within an appropriate range. This is the basis of the familiar idea of a habitable zone around a star. A planet too close to its star may become hot enough for surface water to evaporate. A planet too far away may remain frozen. The habitable zone is useful, but it is not a simple ring with life on the inside and emptiness on the outside. Atmosphere, planetary mass, clouds, rotation, oceans, geology, and the type of star all influence surface temperature. A strong greenhouse effect can warm a distant planet. A reflective atmosphere can cool a closer one. Internal heating can keep underground oceans liquid even far from a star. The Earth itself has not remained continuously comfortable. Its climate has changed greatly. There were periods when ice spread across much of the planet and periods when temperatures were much warmer. Life survived these changes, often in protected environments. This suggests that a living planet does not require perfectly stable conditions, but it does require enough continuity to avoid complete sterilization. A planet also needs access to usable energy. Sunlight is one source. Chemical differences provide another. On Earth, organisms live near deep sea vents without depending directly on sunlight. They use energy released by reactions between chemicals from the planet and substances in the surrounding water. This matters when considering life in other universes or on other worlds. A surface under a bright star is not the only possible setting. Life could develop beneath ice, inside porous rock, or in environments powered by chemical gradients. The range of possible habitats may be much wider than the range represented by Earth's surface. Energy alone is not enough. A system needs a continuing difference between high-quality and low-quality energy. Life survives by taking in concentrated energy and releasing more dispersed energy. Plants absorb sunlight and release heat. Animals consume chemically rich food and produce waste and heat. Cells maintain internal organization by increasing disorder in their surroundings. A universe at complete equilibrium could contain matter, but it would offer no useful flow of energy. Everything would already be evenly distributed. No process could gain a consistent advantage by moving energy from one place or form to another. Chemistry might still fluctuate, but sustained metabolism and information processing would be difficult. The low entropy beginning of our universe created the possibility of long-lasting energy flows. Gravity gathered matter into stars while leaving much of space cold. Stars produced concentrated radiation. Planets received some of that energy and released it at lower temperatures. This difference allows processes to occur. The path toward life therefore depends not only on what matter exists, but also on how energy moves. A collection of carbon, water, and minerals sitting in complete equilibrium is not alive. Living systems maintain themselves by remaining away from equilibrium. They continually exchange matter and energy with their surroundings. Chemistry must also support information. Life on Earth stores instructions in genetic molecules. Those instructions can be copied, but the copying is not perfect. Errors create variation. Some variations help organisms survive and reproduce under particular conditions. Over many generations, natural selection builds complex adaptations. The first systems capable of evolution were probably far simpler than modern cells. Researchers still do not know exactly how life began on Earth. Several stages were required. Simple organic molecules had to form. Some molecules needed to organize into larger networks. Compartments had to keep useful components together. A method of storing and copying information had to emerge. Metabolism and replication eventually became linked. Each stage remains difficult to reconstruct because early evidence has been altered or destroyed. Scientists have shown that many organic molecules can form through natural processes. Amino acids, components of genetic material, and fatty substances can arise under suitable conditions. Meteorites also contain organic compounds, showing that complex chemistry is not limited to living planets. The difficult step is not making one useful molecule. It is creating a system that can maintain itself, reproduce, and evolve. A jar containing amino acids is not close to becoming curious about cosmology. The molecules need organization, a source of energy, and a cycle of reactions that supports continued existence. This uncertainty affects fine-tuning arguments. We do not know how easy or difficult the origin of life is when conditions are suitable. It may occur readily on many planets, or it may require a rare sequence of events. Without a complete theory of life's origin, we cannot define the full range of physical conditions that permit it. The same is true for complex and intelligent life. Simple organisms appeared early in Earth's history, but complex multicellular life took much longer. Technological intelligence appeared only once as far as we know, and it arrived very late. That may indicate that complex intelligence is difficult, or it may simply reflect the particular history of our planet. Several environmental features may have contributed. Earth has a long-lived star, liquid water, active geology, a magnetic field, a large moon, and giant planets elsewhere in the system. Each of these has been proposed as important. Some may help stabilize conditions or reduce certain hazards. Others may be accidental details that life adapted to after they were already present. A magnetic field can reduce the loss of an atmosphere and limit some charged particle radiation, but planets without strong global fields may still retain atmospheres. Plate tectonics helps recycle materials and regulate carbon over long periods, but other geological systems might perform similar roles. A large moon affects tides and Earth's rotation, yet life may not require either feature in the same form. This creates a stack of possible filters. The universe must form stable matter. It must create stars. Stars must make heavy elements. Planetary systems must form. Some environments must support complex chemistry. Life must begin. It must survive. Complex organisms may need to develop, followed by intelligence capable of observing the laws of nature. If each filter is extremely restrictive, observers could be rare even in a vast universe. If most are easy once the earlier conditions are met, life may be common. At present, we do not know the probabilities well enough to multiply them with confidence. The fine-tuning debate often moves too quickly from the existence of physical constants to the existence of human beings. Between those points lies a long history of stars, planets, chemistry, geology, evolution, and chance events. Physics establishes the possible environments, but it does not dictate every biological outcome. An asteroid impact changed the history of life on Earth by contributing to the extinction of many species, including the non-avian dinosaurs. Mammals later expanded into many ecological roles. Without that event, an intelligent technological species might still have appeared, or it might not. Fundamental constants did not specify the exact day of impact or the animals that survived. This mixture of law and contingency is important. The laws of physics create a range of possibilities. Local events determine which possibilities occur. A universe may be well suited to life in principle, while producing very little of it in practice. Another may offer fewer suitable locations, but still develop observers in one fortunate region. Calling the path narrow can therefore mean several things. It may mean that only a limited range of physical constants permit stable complexity. It may mean that suitable planets are rare. It may mean that the origin of a life is difficult. It may mean that intelligent observers require an unusual evolutionary history. These are separate claims and require different evidence. The strongest scientific work tries to separate them. Astrophysics asks which universes can form long-lived stars and heavy elements. Chemistry asks which elements and solvents can support complex reactions. Planetary science examines stable environments. Biology studies the origin and development of living systems. None of these fields has finished its part of the problem. What we can say is that our universe supports a continuous chain from simple particles to observers. The chain contains many conditions, but some are flexible and have alternatives. Stars can regulate themselves. Habitable environments can exist beneath surfaces. Life can use chemical energy as well as light. Organisms can survive conditions that once seemed too hot, cold, acidic, salty, or radioactive. These discoveries have repeatedly expanded the known range of habitability. They encourage caution when declaring that life requires a copy of Earth. At the same time, every alternative still depends on stable matter, workable chemistry, energy flows, and enough time. The details can vary, but the basic need for organised complexity remains. The path may resemble a wide road in some places and a narrow bridge in others. Stellar formation may tolerate large changes, while nuclear stability may impose tighter limits. Chemistry may offer many possible molecules but depend strongly on a few useful elements. Life may survive extreme environments once established while finding its first beginning much harder. Finding the narrowest part of the route is essential to judging the fine-tuning claim. If many different physical settings lead to some form of life, the apparent tuning is weaker. If nearly every change blocks stable complexity at an early stage, the tuning becomes harder to dismiss. There is also a deeper issue. We are evaluating the path from inside its successful outcome. We notice the conditions that led to us because only a successful chain can produce observers able to notice anything. This does not remove the need for explanation, but it changes how the evidence should be interpreted. To understand that selection effect properly, we need to examine the idea that observers can only measure conditions compatible with their own existence. That principle sounds obvious when stated carefully, yet it has produced several competing versions, frequent misunderstanding, and some of the sharpest disagreement in the entire discussion. That disagreement begins with an observation so simple that it can sound almost pointless. Any observer who measures the universe must exist in a part of reality where observers are able to exist. We should not be surprised to find conditions compatible with our presence, because incompatible conditions would prevent us from being here to examine them. This is the basic idea behind the anthropic principle. The name makes it sound as though humanity has been placed at the centre of physics, but its careful use says something much more modest. It does not claim that the universe was made for human beings. It does not claim that life is the purpose of matter. It says that our observations are affected by the fact that we are living observers. Selection effects appear in ordinary situations all the time. Imagine asking why every person interviewed inside a busy railway station happens to be near a railway line. The result is not surprising because the location of the interview selected people who were near the station. It would be a mistake to conclude that most people in the country spend their lives standing beside platforms and wondering why the departure board has changed again. Astronomical observations contain similar effects. Earth is not a random point in space. It is a planet near a stable star. We observe the universe from this location because places without planets, usable energy, and workable chemistry do not contain people building telescopes. Our position is already filtered by the requirements of our existence. This same reasoning applies to the age at which we observe the universe. We could not have appeared during its earliest moments because atoms, stars, planets, and complex chemistry did not yet exist. We also do not find ourselves in a future state where all stars have burned out and usable energy has become scarce. Observers like us naturally appear during a period when the universe has had enough time to create complexity, but still contains active sources of energy. None of that is controversial. The disagreement begins when this obvious selection effect is used to explain the values of fundamental constants. If the strength of gravity, the masses of particles, or the energy of empty space could have taken many values, then only some of those values may permit observers. We will necessarily measure one of the permitted sets, because no measurement is made in the others. At first, this may sound like an answer to fine-tuning. The constants allow life because only a universe with suitable constants can contain someone asking about them. Yet the reasoning leaves an important question untouched. Why does a life-permitting universe exist at all? Suppose you enter a room and find that the temperature is exactly comfortable. Saying that you could not remain in the room if it were dangerously hot explains why you are standing there rather than in a furnace. It does not explain how the room acquired its temperature. There may be a thermostat. The building may have many rooms at different temperatures. The weather may happen to be mild, or you may have arrived during the one comfortable hour of the day. The observation that you can only occupy a survivable room is true under every explanation. It does not choose between them. This distinction separates the weak form of anthropic reasoning from stronger versions. The weak form says that observations must be compatible with the existence of the observer. It is mainly a warning about biased samples. We should not treat our location, time, or physical conditions as though they were selected randomly from every possible environment. A stronger form suggests that the universe must have properties that allow observers to arise at some stage. The word must causes trouble. It can mean nothing more than the logical statement that an observed universe contains conditions under which observation is possible. It can also be interpreted as saying that the universe was somehow required to produce life. Those are not the same claim. Some discussions move even further and propose that observers play a necessary role in bringing reality into a definite form. This idea is sometimes called the participatory anthropic principle. It draws inspiration from questions in quantum mechanics about measurement and observation. However, the word observer in quantum theory does not necessarily mean a conscious person. A measurement can involve a physical interaction that leaves a stable record. A particle does not need to wait patiently for a human being in a laboratory coat before behaving physically. For that reason, claims that consciousness creates the universe go far beyond the ordinary anthropic argument. They may be interesting philosophical ideas, but they should not be confused with the basic selection effect used in cosmology. The most useful anthropic reasoning requires a larger collection of possible environments. If only one universe exists and its constants are fixed, then saying that we observe suitable constants, because we are here, does not explain very much. The statement remains true, but there is no wider population from which observers have been selected. Now imagine that reality contains many regions with different conditions. Some have stronger gravity, some have different particle masses, some expand too rapidly for galaxies to form, others collapse too soon. A smaller group develops stars, planets, chemistry, and living observers. Every observer will find itself inside that smaller group. The situation resembles fish examining the properties of water. Any fish capable of making measurements will report conditions in which fish can survive. It will not report the conditions inside dry sand, even if dry sand is more common across the landscape. The fish has not discovered that the entire world was designed as an aquarium. It has discovered that its sample is limited by where fish can exist. This reasoning can turn fine-tuning into a prediction. Before the accelerated expansion of the universe was firmly established, some researchers considered how large the effect of empty space could be, while still allowing galaxies to form. If the value were far larger, matter would be pulled apart before large structures developed. Observers should therefore expect to measure a value that is not vastly above the limit compatible with galaxies. The observed value is small enough for galaxies to exist, and large enough to influence the present expansion of the universe. Supporters of anthropic reasoning see this as an important success. They argue that a selection effect offered an estimate of the general scale before the relevant observations were complete. Critics point out that the argument depends on assumptions about the possible values, their distribution, the number of observers in different universes, and the connection between galaxies and life. Change those assumptions and the prediction can change. Even so, this example shows that anthropic reasoning does not have to be an empty statement. Under the right conditions, it can influence what observers should expect to measure. The phrase "under the right conditions" is doing a great deal of work. To make a useful anthropic prediction, researchers need to know which physical conditions are possible. They need some way to assign relative likelihoods to those conditions. They need to estimate where observers can arise. Finally, they need to decide what counts as a typical observer. Each step introduces uncertainty. The first problem is the range of possibilities. We do not know whether the constants can truly take different values. A deeper theory may fix them. It may allow a limited collection. It may produce a vast landscape of possibilities. Without that theory, varying a constant is an informative exercise, but not proof that nature can realize the alternatives. The second problem is probability. Suppose many values are possible. Are they equally likely? A number that occupies a small interval may still be common if the physical process that produces universes strongly favors that interval. A broad interval may be rare if almost no universe-forming process reaches it. Returning to the room analogy, a comfortable temperature may occupy only a narrow part of the thermometer. That fact does not make it improbable if nearly every room has a heating system that aims for that range. The size of the allowed range and the chance of entering it are different questions. The third problem concerns observers. Life may be possible under conditions very different from those on Earth. If researchers count only planets similar to our own, they may underestimate the true observer-friendly region. If they count every stable arrangement of matter as a possible observer, the estimate becomes so broad that it loses contact with biology. An observer needs some ability to receive information, preserve records, and respond to its environment. That definition may include animals, intelligent machines, unfamiliar forms of life, and systems that have never appeared on Earth. Physics does not yet provide a complete account of consciousness or observation, so cosmological arguments often use simpler substitutes. They may count galaxies, stars, planets, or the production of heavy elements. These substitutes are practical, but they are not the same as counting observers. A galaxy can contain no life. A planet can remain sterile. A universe with fewer galaxies might produce more life if those galaxies are unusually stable. The relationship between cosmic structure and observation is indirect. Then comes the problem of typicality. Should we assume that we are typical among all observers? This assumption is often hidden inside anthropic arguments. If most observers measure one range of values, we may expect to measure something similar. Yet there is no guarantee that we occupy the most common situation. People are often unrepresentative samples. Someone listening to a long physics video near bedtime is not a random human activity chosen from the entire population. It reflects interests, technology, language, free time, and perhaps a desire to fall asleep while someone calmly explains cosmology. Being unusual does not make the observation impossible. In cosmology, the issue becomes more serious because the collection of observers may be infinite. If a model creates endlessly many regions, then every permitted kind of event may happen endlessly many times. Comparing one infinity with another is not straightforward. Researchers need a procedure for regulating the count and assigning relative weights. This is known as the measure problem. Different methods of counting can produce different predictions. One procedure may say that most observers should see a young universe. Another may favour older regions. Some measures produce strange results that conflict with what we observe. Finding a method that is mathematically consistent and physically justified remains difficult. An especially odd consequence appears in some models that last for an extremely long time. Random fluctuations could occasionally assemble a brief thinking system complete with false memories. Such an observer might exist only for a moment in otherwise disordered space. These hypothetical entities are often called Boltzmann brains. The name is memorable, though the idea is less entertaining than it sounds. If a cosmological model predicts vastly more temporary fluctuating observers than ordinary observers produced by stars, planets, and evolution, then a typical observer in that model should expect to be one of the temporary kind. We do not seem to observe a chaotic environment with invented memories. We see an orderly universe that follows stable patterns. This creates a test of cosmological theories. A model that predicts that almost every observer is a random fluctuation may be considered unacceptable or incomplete. The anthropic approach therefore does not merely excuse any possible observation. It can reveal problems when a theory makes our orderly experience extraordinarily atypical. Still, critics worry that anthropic explanations can be used too easily. Whenever a value seems puzzling, someone may say that observers require it. That can stop the search for a deeper mechanism. If earlier scientists had used anthropic reasoning to explain every feature of nature, they might never have discovered the processes behind planetary motion, atomic structure, or biological adaptation. Supporters answer that selection effects are not replacements for physical theories. They are part of interpreting what a theory predicts. If a multiverse theory produces different constants in different regions, ignoring the locations where observers can exist would lead to incorrect conclusions. The anthropic principle is not supposed to explain how universes form. It helps connect a theory about many universes to the measurements made by beings inside them. This is a reasonable distinction, although it does not end the dispute. A deeper explanation is usually preferred when available. Physicists want mechanisms that can be tested independently, not only arguments based on the conditions needed for observers. The question is what to do when a theory naturally produces many environments and no single set of constants is selected in advance. There are historical examples where selection effects provide genuine understanding. The distance between Earth and the Sun falls within a range that permits liquid water under suitable atmospheric conditions. We no longer assume that this distance was fixed by a universal law, requiring every planet to be habitable. Planetary systems contain many orbits. Observers naturally arise, if they arise at all, on planets in suitable locations. The same applies to the position of the Sun within the galaxy. We are not at the crowded centre, where radiation and gravitational disturbances may create difficult conditions. We are not far beyond the main stellar disk, where heavy elements are scarce. Our location may partly reflect the environments in which long-lived planetary systems can develop. These examples work because we have evidence for many planets, stars, and galactic locations. The selection population is observable. We can compare inhabited conditions with a real variety of alternatives, even though we have not yet confirmed life elsewhere. Applying the same reasoning to fundamental constants requires a much larger step. We have not observed universes with different constants. The multiverse may be implied by theories, but it is not available through an ordinary telescope. This makes the anthropic explanation less secure than the explanation for Earth's orbit. The difference does not make it unscientific automatically. Science often studies entities that cannot be observed directly when they produce indirect effects or arise from strongly supported theories. The interior of a black hole cannot send us a report. The earliest moments of cosmic history are not visible in the ordinary sense. Researchers infer them from consequences that can be measured. A multiverse becomes scientifically interesting if it emerges from a theory that also makes testable predictions about our observable region. If that theory succeeds repeatedly, and the wider collection is an unavoidable consequence, then anthropic selection may become part of its interpretation. If the multiverse is added only to explain fine-tuning and produces no other evidence, critics will remain unconvinced. There is also a philosophical concern. Some people hear the anthropic principle and think it says the universe exists because we are here. The careful argument runs in the opposite direction. We are here because this region of reality permits us. The observer does not normally cause the conditions. The conditions filter which observers can appear. Imagine puddles forming after rain. A puddle fits the hollow beneath it closely. It would be a mistake for the puddle to conclude that the ground was shaped specifically for its outline. Water collects in places where the terrain allows it. This analogy is often used against design arguments, though it has limits. Living organisms are not passive liquid. They evolve, adapt, alter their surroundings, and require complicated physical processes. Adaptation explains why organisms fit local environments. It does not explain why the universe permits organisms chemistry or evolution in the first place. The puddle analogy is useful for local biological fit but cannot settle the question of fundamental constants. Another common misunderstanding treats the anthropic principle as proof that life must appear whenever conditions permit it. That does not follow. A universe may contain stable stars and rich chemistry without ever producing life. The anthropic argument says that observers can only appear where conditions allow them. It does not say that every allowed location develops observers. This creates a difference between necessary and sufficient conditions. Stable atoms are necessary for known life, but they are not sufficient. A box of carbon does not begin writing a diary simply because its atoms remain intact. Long-lived stars may be necessary for many forms of life, but they do not guarantee biology. A suitable planet may remain lifeless for its entire history. Anthropic reasoning often identifies necessary conditions because those are easier to study. It can tell us that observers cannot exist where all matter is unstable or where the universe collapses almost immediately. It is much less capable of telling us how frequently life begins once those basic barriers are removed. The principle is therefore both useful and limited. It reminds us that our observations come from a selected location. It can help turn theories with many environments into predictions. It can rule against models in which our experience would be overwhelmingly abnormal. It cannot by itself explain why a collection of universes exists, why it has a particular distribution, or how consciousness emerges. Whether it resolves fine-tuning depends on what lies behind it. If there is one universe with one unexplained set of constants, anthropic reasoning offers little more than a reminder that unsuitable conditions would not be observed. If there are many regions with varied constants generated by a well-supported physical process, then the principle becomes much more powerful. It can explain why observers measure rare life-permitting values without claiming that those values are typical across all reality. The debate has now reached the point where one question becomes unavoidable. Is there any scientific reason to think that such a collection of universes exists? The answer is not a single proposal, but several very different ideas that share the same convenient name. Some come from the rapid expansion thought to have occurred in the early universe. Some come from attempts to unify particles and forces. Others arise from interpretations of quantum mechanics. They do not all contain the same kinds of universes, and they do not all solve the same problem. To decide whether anthropic selection offers a real explanation rather than a verbal escape route, we have to look at how a multiverse might be produced, what could vary within it, and whether a collection beyond our visible horizon can ever become part of testable physics. The first difficulty is that the word multiverse does not refer to one agreed scientific model. It is a general label for several ideas in which the reality we observe is only part of a larger structure. Those ideas come from different areas of physics, make different claims, and do not always fit together. Grouping them under one name is convenient, but it can create the false impression that physicists have developed a single multiverse theory and are now arguing only about whether to believe it. Some versions contain distant regions governed by the same laws as ours. Other versions allow the constants of nature to differ from one region to another. Some describe separate expanding bubbles in a larger cosmological process. Another version comes from an interpretation of quantum mechanics and does not require bubbles, distant locations, or different physical constants at all. The simplest possibility begins with the size of space. The observable universe is limited because light has had only a finite amount of time to reach us. We can see galaxies only if their light has been able to travel to our location since the early universe. Beyond that visible region, space may continue much farther. It may even continue without an end. If space extends beyond what we can observe, then there are regions we cannot currently see. Those regions would not necessarily be separate universes in a dramatic sense. They could simply be more of the same universe, located beyond our cosmic horizon. They might contain galaxies, stars, and planets formed under the same laws of physics. Calling these regions other universes is partly a matter of language. They are not separated from us by a wall. They are separated by distance and by the behavior of expanding space. Light from some regions may never reach us because the space between us and them is expanding too quickly. This type of multiverse does not immediately explain fine-tuning. If the laws and constants are the same everywhere, then adding more space produces more planets and more opportunities for life, but it does not explain why the basic laws allow any of those things. A larger universe gives nature more attempts to produce rare events. It does not change the rules governing each attempt. A more relevant proposal comes from cosmic inflation. Inflation is the idea that the early universe experienced a brief period of extremely rapid expansion. It was introduced to explain several features of the observable universe, including its large-scale uniformity and the way small early variations could become the seeds of later cosmic structure. In the usual picture, inflation stretched a very small region into something much larger. Tiny irregularities were also stretched, and later grew into galaxies and clusters under gravity. The broad idea has produced successful predictions, although physicists still debate the exact mechanism and the field or process that caused inflation. Some models do not allow inflation to end everywhere at once. It ends in certain regions while continuing in others. A region where inflation ends can develop into a universe like the one we observe, with hot matter, radiation, expansion, stars, and galaxies. Meanwhile, the surrounding space continues inflating and producing more regions where inflation may later end. This process is called eternal inflation. The word eternal refers to the continuing process as a whole, not necessarily to the past history of every region. Individual regions can leave the inflating state, but the total inflating volume can keep growing faster than it disappears. New regions continue to form even while older ones develop independently. These regions are often described as bubble universes. The image is useful, provided we do not imagine ordinary soap bubbles floating through an already existing room. The larger inflating space is not a container in the everyday sense. The bubbles are regions in which the physical state of space has changed. Inside one bubble, inflation may end and release energy into particles and radiation. The region then begins a history that can include the familiar stages of cosmic evolution. From the viewpoint of someone inside it, the bubble may appear enormous and possibly spatially unlimited. The fact that it began as a small region from an outside description does not mean its inhabitants would see a curved wall sitting somewhere beyond the nearest galaxy. Different bubbles may settle into different physical states. If the underlying theory allows several stable or long-lived states, then the particles, forces, and constants measured inside one bubble could differ from those measured inside another. Gravity might have a different relative strength. Particle masses might change. The energy associated with empty space could take another value. This is where eternal inflation becomes relevant to fine-tuning. It provides a possible mechanism for creating many regions with varied conditions. Most of those regions might never form galaxies. Some might contain no stable atoms. Others could produce stars but little useful chemistry. Observers would appear only in the smaller collection where the conditions permitted organized complexity. The anthropic principle would then act as a selection rule. we would not need to claim that our constants are typical across the whole multiverse. We would only expect them to fall within a range compatible with observers. A rare, life-permitting region would not be surprising to the creatures inside it, even if almost every other region were empty. This explanation needs more than a large number of bubbles. It needs variation. If every bubble has the same constants, the original question remains. Eternal inflation can create a vast population of regions, but another part of the theory must explain why those regions can settle into different physical states. String theory is often introduced at this point. It is an attempt to describe particles and forces through basic objects, whose different patterns of behavior appear as different particles. The theory also includes gravity in a quantum framework, which is one reason it has attracted so much attention. Many versions of string theory require additional spatial dimensions beyond the 3 large dimensions we experience. Those extra dimensions may be compact and extremely small. Their shape and arrangement influence the physical behavior seen at ordinary energies. Different ways of arranging the extra dimensions can produce different effective particles, forces, masses, and vacuum energies. The equations do not appear to select one obvious arrangement corresponding uniquely to our universe. Instead, they may allow a very large collection of possible states. This collection is known as the string landscape. Each point in the landscape represents a possible vacuum state with its own low-energy physics. The word vacuum does not mean a completely empty space. It refers to the underlying state of fields and geometry from which particles and interactions emerge. Some proposals within string theory allow a huge number of these states. Multiple quantized fields can contribute different amounts to the energy of empty space, producing a dense range of possible values. This offers a possible way to obtain regions where the cosmological constant is very small, without requiring every contribution to cancel in exactly one predetermined way. Eternal inflation and the string landscape are often joined into one picture. Inflation creates many bubbles, and different bubbles settle into different states from the landscape. The landscape supplies the menu of possible laws, while eternal inflation keeps opening new restaurants. Most of them may have terrible reviews, no stable tables, and a menu consisting entirely of particles that decay before the waiter arrives. A small fraction could have constants that permit atoms, stars, chemistry, and observers. From inside one of those regions, the local laws would appear fixed. We would not see constants changing from day to day because our entire observable history developed within one vacuum state. This combined picture is attractive because it connects several problems. It may explain why there are many environments, why constants vary, and why observers measure a life-permitting set. It may also offer an approach to the unusually small observed effect of vacuum energy. Attractive does not mean established. String theory has not yet produced a unique confirmed description of our universe. The landscape is difficult to calculate fully, and researchers disagree about which proposed states are stable and physically meaningful. Eternal inflation also depends on assumptions about high-energy fields that have not been directly observed. Joining two uncertain ideas does not automatically create one certain idea. It creates a larger proposal with interesting possibilities and a longer list of jobs still waiting to be completed. The number of possible states is also easy to misunderstand. Popular descriptions sometimes say that the landscape contains every imaginable universe. That is not what the theory claims. It would contain only states allowed by its mathematical structure. There may be many of them, but many is not the same as everything. A universe in which gravity suddenly becomes embarrassed and stops working on Tuesdays is not included merely because someone can imagine it. The possible states must follow the underlying theory. Even a very large landscape may occupy a restricted part of everything that can be described in words. Another proposed multiverse comes from quantum mechanics. It is usually called the many worlds interpretation. This idea is different from the bubble picture, though the two are often mixed together in popular discussions. Quantum mechanics describes physical systems through a state containing several possible outcomes. In a laboratory measurement, we observe one result. The usual question is what happens to the other possibilities. Some interpretations say that the quantum state changes during measurement, so that only one outcome remains. The many worlds interpretation says that the quantum state continues according to the same underlying rule without a special collapse. Different outcomes become associated with different branches that no longer interfere with one another in ordinary conditions. An observer inside one branch experiences one definite result. Another version of the observer is associated with another result. The branching is not caused by a human decision. It comes from quantum interactions and the spread of information into the surrounding environment. Choosing tea rather than coffee does not create a new universe simply because the choice feels important before breakfast. The relevant branching began through countless physical interactions before the choice reached conscious awareness. Human decisions are part of the process, not the special trigger for it. These quantum branches are not bubbles expanding in distant space. They are components of a universal quantum state. Travelling far enough in one branch would not take you into another. The separation is connected to the loss of observable interference between complex alternatives, not to an ordinary gap measured in kilometres. Many worlds also does not automatically solve fine-tuning. The branches usually share the same underlying laws and constants. They contain different outcomes of events governed by those laws. One branch may contain a particle detected in one place, and another branch may contain it elsewhere, but both branches use the same particle physics. To explain different constants, the universal quantum state would need to include different vacuum states or cosmological histories. Some theoretical pictures combine quantum branching with inflation and a landscape, but the many worlds interpretation alone does not provide every possible set of laws. The interpretation remains debated because it raises difficult questions about probability. If all allowed outcomes occur, what does it mean to say that one outcome is more likely than another? Supporters argue that the usual quantum probabilities can be recovered through the structure of the branches and rational expectations. Critics question whether the explanation is complete or unique. There is no simple experiment that distinguishes every version of many worlds from every competing interpretation, while all of them reproduce ordinary quantum predictions. The disagreement is partly about what the mathematical description says reality is, rather than about calculations that give different laboratory results. This makes the quantum multiverse less directly useful for the fine-tuning argument than eternal inflation combined with varied vacua. It may still be part of a larger picture, but it should not be used as a convenient box containing any universe needed for an explanation. Other multiverse proposals exist as well. Some cosmological models describe repeated cycles in which expanding phases follow earlier phases. Some suggest that new expanding regions could form through processes associated with black holes. Others imagine universes reproducing with slightly varied properties, creating a form of cosmological selection. These ideas differ greatly in their mathematical development and evidential support. They are not interchangeable. A cyclic universe may repeat similar laws rather than explore varied constants. A black hole proposal may produce related universes with inherited properties. Neither one provides an automatic answer to fine-tuning simply by increasing the number of cosmic regions. The central scientific question is not whether a multiverse sounds strange. Many accepted ideas in physics sounded strange before evidence supported them. The relevant question is whether a multiverse follows from a theory that explains observations and makes successful predictions. Direct observation is difficult because other universes are usually defined as regions outside our causal reach. No signal can travel to us from a completely disconnected region. Critics argue that a proposal involving permanently unobservable universes risks moving beyond experimental science. Supporters respond that unobservable entities can still be part of a testable theory. We do not observe every consequence of a theory directly. We test the predictions available within our region, and then consider the full structure implied by the equations. If eternal inflation follows unavoidably from a model that is strongly supported by observations, its other regions may deserve the same serious consideration as other inaccessible consequences of successful theories. The strength of that argument depends on how unavoidable the multiverse really is. Inflation, as a broad idea, does not guarantee eternal inflation. A particular model may produce it, while another may not. Evidence supporting an early period of rapid expansion would not by itself confirm every eternal model. Researchers have considered whether collisions between bubble universes could leave observable traces. If another bubble interacted with ours early enough, the collision might disturb the distribution of matter and radiation. It could produce a structured pattern in the cosmic microwave background, the ancient radiation left from the early universe. Searchers have looked for such patterns. No confirmed bubble collision has been found. The absence of a signal constrains some models and possible collision rates, but it does not eliminate eternal inflation as a whole. A collision may have occurred outside our observable region, may have left a signal too weak to detect, or may be unlikely in the relevant model. Theoretical work nevertheless shows that bubble collisions can, under some assumptions, produce calculable observational signatures. This illustrates both the promise and the difficulty of testing a multiverse. A detected collision with the predicted features would provide powerful evidence. A failure to detect one rules out only the models that expected a visible signal. The larger concept can remain while individual versions are removed. Another major problem appears when the multiverse contains an unlimited number of regions. Eternal inflation can produce infinitely many bubbles, and each type of allowed event may occur infinitely many times. We can no longer calculate probabilities by simply counting how often something happens. Suppose there are infinitely many life-permitting bubbles and infinitely many sterile bubbles. Saying that both numbers are infinite does not tell us which kind is more common. Researchers must introduce a measure, a method for regulating the infinities and comparing different classes of observers or regions. Different measures can produce different answers. One method may favour universes that form quickly. Another may favour regions with greater volume. Some methods produce too many young universes, too many unusual observers, or other predictions that do not resemble our experience. There is no universally accepted solution to this measure problem. It is not a minor technical inconvenience. The anthropic explanation depends on probabilities, and those probabilities depend on how the multiverse is counted. Without a justified measure, it is difficult to say whether our observed constants are expected or extremely unusual within the model. The problem becomes sharper when observers are included. A universe with many galaxies may contain few observers. Another with fewer galaxies may produce large civilizations or vast numbers of artificial minds. Should each universe count once? Should each galaxy count? Or should every observer count separately? Counting observers creates its own puzzles. Very long-lived universes may produce rare random fluctuations that briefly form systems with memories and thoughts. If those temporary observers greatly outnumber ordinary biological observers, then the theory predicts that a typical observer should have disordered experiences. Our observations of a consistent external world would become difficult to explain. A successful multiverse theory must therefore do more than produce at least one universe like ours. It should make our general observations reasonably typical among the observers the theory predicts. Otherwise, the explanation can accommodate our existence but cannot explain why we see the particular ordered environment around us. There is also a danger of flexibility. If a theory contains enough possible universes, almost any observation may occur somewhere. A theory that allows everything can become difficult to test unless it also tells us what observers are likely to see. The useful statement is not that our universe exists somewhere in the collection. The useful statement is that observers produced by the theory would usually, or at least reasonably often, measure properties like the ones we measure. Reaching that statement requires a mechanism for generating universes, a distribution of physical constants, an account of observer selection, and a reliable measure. None of those tasks has been completed in a generally accepted way. The multiverse remains a serious area of theoretical research, but it is not a confirmed discovery. It offers a possible explanation for fine-tuning rather than a demonstrated solution. Its appeal is easy to understand. If there are enough varied universes, a life permitting one no longer needs to be typical. The appearance of delicate adjustment can result from observing only the environments in which observers survive. This is similar to explaining Earth's suitable orbit by the existence of many planets, rather than by a law forcing every planet to orbit at the same distance. The weakness is equally clear. We have direct evidence for many planets. We do not have direct evidence for a population of universes with different constants. The proposed population comes from theories that remain incomplete and difficult to test at the energies involved. Rejecting the multiverse because it feels excessive would not be a scientific argument. Accepting it because it solves an uncomfortable problem would not be one either. Its value depends on whether it emerges naturally from successful physics, whether its predictions can be defined, and whether observations can distinguish it from alternatives. Fine-tuning therefore places the multiverse in an unusual position. It is not merely an imaginative addition to cosmology. It can arise from serious attempts to understand inflation, quantum theory, and high-energy physics. At the same time, it asks us to explain what we observe by appealing to a collection that may remain mostly inaccessible. That leaves several competing possibilities still on the table. The constants may be necessary consequences of a deeper law. They may be environmental values selected from a multiverse. They may be unexplained facts. They may reflect some form of intention. The appearance of tuning might even weaken as our understanding of stars, chemistry, and possible life improves. Choosing among those possibilities requires more than asking which one sounds most comfortable. We need to compare what each explanation actually says, what evidence would support it, what assumptions it introduces, and where it moves the unanswered question. That comparison is where chance, physical necessity, design, and incomplete knowledge finally meet. That meeting begins with a useful question. What would count as an explanation? The constants of nature have particular values. Those values allow stable matter, long-lived stars, complex chemistry, and at least one planet where life developed. We can describe that sequence in great detail, but description is not the same as explanation. A complete explanation would tell us why these values occur, whether they could have been different, and why the universe contains conditions that allow organized structures to appear. There are several broad answers. The values may be the result of chance. They may be fixed by a deeper physical law. They may vary across a larger multiverse, with observers appearing only in suitable regions. They may reflect intentional design. There may also be an explanation that does not fit any of these categories, because our current theories are missing something basic. Each answer has strengths and difficulties. None has been confirmed. The disagreement continues because the same observations can be interpreted in different ways, depending on what a person thinks a successful explanation should accomplish. Chance is often presented as the simplest possibility. The constants have the values they have, and no further reason exists. They were not selected by a process, derived from a deeper law, or chosen for a purpose. Our universe simply began with this set of properties. This may sound unsatisfying, but dissatisfaction does not make an explanation false. Every chain of reasoning must eventually reach something that is accepted without a deeper cause. If we explain the constants using another law, we may ask why that law exists. If we explain the law using a more fundamental structure, we may ask why that structure exists. Continuing to ask why does not guarantee that reality contains an answer at every level. A basic fact is not automatically a bad scientific idea. Physics already contains measured properties that are treated as inputs. Researchers determine them through observation and use them to make predictions. The predictions can be extremely accurate even when the underlying value remains unexplained. The problem with chance appears when people attach probabilities to it. Saying that our universe occurred by chance suggests that other values were possible, and that some process selected among them. To decide whether the result was unlikely, we would need to know the possible range and how often each outcome occurs. We do not have that information. There is no confirmed probability distribution for fundamental constants. We cannot say that every possible strength of gravity was equally likely. We do not know whether the constants could vary continuously, whether only a limited set was possible, or whether their observed values were the only consistent ones. An event can look extremely unlikely under one assumed distribution and completely ordinary under another. Imagine finding a book open to page 200. If someone opened it randomly, the result may be one among hundreds. If the book has a heavy bookmark on that page, the outcome is not surprising. Without knowing the mechanism, the open page does not reveal the probability. For this reason, statements giving precise odds for a life-permitting universe should be treated carefully. They often depend on assumed ranges and assumed ways of assigning probability. Those assumptions may be useful for exploring sensitivity, but they are not measurements of an actual universe-producing process. Chance can also mean something more limited. Perhaps the laws are fixed, but the initial conditions were not. The early distribution of matter, the level of density variation, or the state of certain fields may have emerged from physical processes that include random quantum behavior. In that case, some cosmic features could be genuinely probabilistic even if the deeper laws remain stable. Quantum mechanics gives reliable probabilities for experiments when the physical state and measurement arrangement are known. Applying the word chance to the origin of all physical laws is more difficult. There is no external laboratory preparing universes for repeated trials. We cannot assume that cosmic chance works like a familiar experiment unless a theory tells us why. A different answer says that the constants are not accidental at all. They may be necessary consequences of a deeper theory. What appears to be a collection of adjustable values could follow from one basic structure. This possibility has strong appeal within physics. The history of the subject includes many successful unifications. Electricity and magnetism were once studied as separate phenomena before they were understood as parts of one interaction. Different chemical substances were explained through combinations of a limited set of atoms. The behavior of heat was connected to the motion of particles. Each unification reduced the number of independent facts. A future theory might do the same for particle masses, force strengths, and the properties of empty space. Instead of measuring many unrelated constants, physicists could derive them from a smaller set of principles. If such a theory allowed only one consistent universe, the fine-tuning problem would change. Asking why the constants fall within a life-permitting range would be similar to asking why a triangle has properties that follow from its definition. The values would not have been selected from alternatives. They would be required by the structure of reality. This would explain why the dials have their positions, but it would create another question. Why does the unique theory permit life? Some people would regard that as a remarkable coincidence at a deeper level. Others would say the question has reached its endpoint. If mathematical and physical consistency lead to one possible universe, then the existence of observers is simply one consequence of that universe. There is no guarantee that a final theory would be unique. It might allow many solutions. It might contain parameters that still need to be measured. It could explain some constants while leaving others free. Progress may reduce the apparent tuning without eliminating it. The search for deeper necessity is therefore a real scientific program, not merely a philosophical hope. Researchers try to unify interactions, understand particle masses, describe quantum gravity, and explain cosmic expansion. A successful theory would need to reproduce known physics and make predictions that can be tested. At present, no accepted theory derives every relevant feature of our universe from one unavoidable principle. This does not mean the project has failed, it means the answer remains unknown. The multiverse offers another way to combine chance with physical law. A deeper theory may allow many possible states, and a cosmological process may realize them in different regions. The underlying mechanism follows laws, while the local constants vary. Under this picture, our universe is not a single unlikely event with no context. It is one member of a large population. Most regions may not support complex structures. Observers naturally appear in the smaller set where stable matter, stars and chemistry are possible. This explanation has an advantage. It does not require the local constants to be uniquely determined. It also does not require someone to choose them. They are apparent tuning results from selection. We measure suitable values because unsuitable regions contain no one making measurements. The multiverse also carries serious burdens. The generating mechanism must be physically credible. The possible states must be defined. Probabilities must be assigned. The selection of observers must be handled without making every observation equally acceptable. If the theory predicts that observers like us are extremely rare even within the life-permitting regions, it has not fully explained what we see. If different methods of counting universes give different answers, the predictions remain uncertain. If no observation can distinguish the proposal from a single universe, the scientific status becomes difficult to evaluate. Supporters argue that these problems may be solved as the underlying theories improve. Critics argue that the flexibility of the multiverse can protect it from failure. A poor prediction can be blamed on the probability measure, the assumed landscape, or the definition of observers. This disagreement does not have to be settled by declaring the entire idea scientific or unscientific in one sentence. Specific multiverse models can be evaluated individually. A model that makes clear predictions can be tested. A model that explains any result has less value. The word multiverse is too broad to receive one verdict. Then there is design, the explanation that produces the most debate outside physics, and some of the most careful avoidance inside it. The design argument begins with the claim that life-permitting conditions are unlikely under chance and not yet explained by necessity. It then suggests that intentional selection may provide a better explanation. The constants have suitable values because an intelligent cause intended a universe capable of life. This argument is not identical to the claim that every feature of nature is perfect. A designed system can contain empty space, destructive events, and environments hostile to life. The narrower claim is that the basic laws were selected to make life possible somewhere. Design has an immediate intuitive attraction. In ordinary life, when several conditions work together toward a recognizable outcome, intention is one possible explanation. A radio adjusted to one station, a machine with fitted parts, or a message arranged into meaningful words often points to deliberate action. The difficulty lies in transferring that reasoning to the universe as a whole. In ordinary cases, we recognize design because we have experience with both designed and undesigned objects. We know that people build radios. We can visit factories, observe engineers, and compare manufactured devices with naturally occurring materials. We do not have a comparable sample of universes. We have not observed universes being designed and undesigned. We do not know what an intentionally created universe should look like, compared with one produced by an unknown physical process. A design proposal must also say enough to be evaluated. What was the goal of the designer? Was it any form of life, conscious life, human life, mathematical complexity, or something else? Would different constants have served that goal more effectively? Why is most of the observable universe unsuitable for biology as we know it? Possible answers can be given, but each additional answer introduces assumptions about the intentions and abilities of the designer. Those assumptions are difficult to test through physics. Design can explain any set of constants by saying that they were intended. This broad compatibility is both its strength and its weakness. It can account for a life-permitting universe, but it may also account for a sterile one by proposing a different intention. A scientific explanation becomes useful when it excludes some observations and predicts others. Suppose a theory says that a certain particle must exist within a limited range of mass. Experiments can search for it. Failure to find the particle can count against the theory. A general design claim may not provide a similar test because any result can be included within an unknown plan. This does not prove that design is false. It means that design may function as a philosophical or theological explanation rather than as a physical theory. science has methods for testing regular processes within nature. It is less equipped to examine an intentional cause placed outside or beneath those processes. Some design advocates try to make the argument probabilistic. They compare the likelihood of life permitting constants under chance with the likelihood under design. If a designer wanted life, suitable constants would be expected. If constants were random, suitable values might be rare. The comparison faces several problems. We do not know the probability of the constants under chance. We also do not know the probability of a designer choosing these constants. A designer might prefer a universe with more life, less empty space, different laws, or no physical universe at all. Without knowing the designer's goals, the prediction remains uncertain. The argument can still have philosophical force for people who already accept other reasons for believing in a creator. Fine-tuning may fit within that wider view. For someone who does not accept those assumptions, the same evidence may not point in the same direction. This is why fine-tuning rarely acts as a neutral machine that receives data and prints out one conclusion. The interpretation depends partly on background beliefs about explanation, probability, and what kinds of causes are possible. Scientists also worry that design can stop inquiry too early. If a difficult feature is attributed to intention, researchers may feel less pressure to find a physical mechanism. The history of science includes many phenomena once explained through purpose that later received detailed natural explanations. Planets do not move along their paths because they aim for perfect circles. Species are not individually shaped in advance for each environment. Weather does not occur to reward or punish a village. Physical and biological processes explain these patterns without requiring local intention. This history encourages caution, but it does not settle the origin of the laws themselves. Explaining events within the universe is not the same as explaining why the universe has any laws. A person can accept every natural mechanism discovered by science and still ask whether the whole structure has a deeper cause. The important boundary is between asking the question and claiming that physics has answered it. Physics can show which constants affect life. It can test models that derive or vary those constants. It cannot currently detect an intention behind them. There is another option that often receives less attention because it does not offer a clear final picture. Our entire way of framing the problem may be incomplete. We speak of constants as if they were independent knobs. They may instead be consequences of relationships we have not discovered. We speak of possible universes as if we know the full range. Our present theories may describe only a small area of what physical consistency allows. We speak of life as if carbon chemistry on planets is the standard by which every universe should be judged. Other kinds of organized systems may exist under conditions we currently call sterile. We speak of probability even though there may be no meaningful process assigning equal chances to different laws. Several apparent fine-tuning problems have already changed as models improved. Early arguments sometimes held one quantity fixed while changing another. Later studies allowed stars to adjust or several parameters to vary together. Regions that first appeared completely lifeless became more complicated and sometimes more permissive. The reverse can also happen. A universe may appear suitable when only one stage is considered, but fail at a later stage. It may form stars but no useful heavy elements. It may produce chemistry but no stable energy sources. It may create planets that lose their atmospheres quickly. Better knowledge can widen or narrow the allowed region. We should not assume in advance which direction the final result will move. The unknown explanation could involve new physics at extremely high energies. It could connect quantum theory with space-time. It could change our understanding of initial conditions. It could reveal that what we call constants vary through a deeper process while appearing stable in our region. It could also show that the universe is not a single basic object. Space, time, matter, and physical laws may emerge from something more fundamental. In that case, asking why the constants were adjusted might resemble asking why the wetness of water was adjusted before molecules existed. The question would use concepts that apply at one level to describe a deeper level where those concepts do not yet exist. This possibility is not an answer by itself. Saying that future physics will solve the problem is not a theory. It is a reminder that unfinished science should not be treated as final evidence for any conclusion. There is a natural temptation to choose among chance, necessity, multiverse selection, and design according to personal preference. Chance can feel empty. Necessity can feel elegant. The multiverse can feel excessive. Design can feel meaningful or unacceptable depending on the listener. Feelings can guide interest, but they do not decide which explanation is correct. The universe has no obligation to be simple, comforting, or easy to test. It may contain a vast multiverse. It may follow one unavoidable law. It may rest on facts with no deeper explanation. It may involve causes that science cannot currently examine. A fair comparison asks several questions. Does the explanation fit what we observe? Does it introduce assumptions that have independent support? Does it make predictions? Could evidence count against it? Does it explain the constants or merely move the question somewhere else? Chance introduces few extra entities, but it may leave the apparent tuning unexplained. A unique deeper law could provide a strong explanation, but no such complete law is known. The multiverse gives anthropic selection a physical setting, but its probabilities and tests remain unsettled. Design provides intention, but the intentions and mechanism are not independently measurable. The unknown option is honest but incomplete. It protects us from premature certainty while offering no prediction of its own. It is possible that the final explanation will combine several ideas. A deeper theory might generate many possible states. A cosmological process might select among them partly through chance. Observers might appear only in a restricted subset. What looks like one question could have answers at several levels. Consider a shuffled deck of cards. The rules of the deck determine which cards exist. The shuffle determines their order. A player selects a hand according to the game. The final arrangement reflects necessity, chance, and selection at once. Asking which one caused the hand has no single answer, because each operated at a different stage. The universe may work in a similarly layered way. Fundamental consistency could determine a range of possibilities. Quantum processes could influence which state develops. Anthropic selection could explain why observers occupy only some outcomes. Even then, a person might continue asking why that larger structure exists. At some point, scientific questions meet philosophical ones. This does not mean science has failed. It means that different methods address different parts of the problem. Experiments can measure constants. Models can test their effects. Cosmology can investigate the early universe. Philosophy can examine what counts as explanation and whether probability applies to a single universe. Confusion begins when conclusions from one method are presented as though they were established by another. A mathematical sensitivity does not prove design. The absence of a known designer does not prove chance. The possibility of a multiverse does not confirm that one exists. The hope for a unique theory does not make the constants necessary. The evidence currently shows that several physical features are important for stable complexity. Some appear sensitive to change. Others permit wider variation than simple arguments suggest. We do not know the complete set of possible laws or the probability of different values. That leaves the central controversy unresolved, but it also makes the final evaluation clearer. The important question is no longer whether someone can list constants that affect life. Many constants do. The important question is whether the dependence is narrow enough, independent enough, and improbable enough to justify calling the universe genuinely fine-tuned. Answering that requires separating strong evidence from exaggerated examples, distinguishing physical sensitivity from probability, and deciding whether the term fine-tuning describes a discovery, a warning about our theories, or an interpretation placed on facts that remain incomplete. That final question sounds as though it should have a simple answer. Either the universe is fine-tuned or it is not. Yet the closer we look, the more we find that several different questions have been placed under the same label. Does the universe contain physical values that strongly affect stars, atoms, chemistry, and cosmic structure? Yes. Would changing some of those values produce a universe very different from ours? Yes. Do certain combinations appear to make stable complexity more difficult or impossible? Yes. Does that prove that the values were selected from a wide range of equally likely alternatives? No. Does it prove intention, chance, a multiverse, or a unique deeper law? No. The safest conclusion is that the universe shows real sensitivity to several fundamental physical features, but we do not yet know enough to calculate how surprising those features are. Fine-tuning is therefore a serious scientific and philosophical problem, but it is not a completed argument with one unavoidable conclusion. This may sound less exciting than announcing that the universe was balanced with impossible precision. It may also sound less satisfying than dismissing the entire subject as a misunderstanding. Unfortunately, the evidence does not appear interested in making the discussion easy. Some examples of fine-tuning are stronger than others. The energy associated with empty space remains one of the most difficult. Simple expectations from quantum field theory do not naturally match the small cosmic effect we observe. A much larger positive value could prevent galaxies from forming. A sufficiently negative value could cause the universe to collapse too quickly. This is a genuine problem in physics even before life is mentioned. The theoretical contributions seem to require an enormous cancellation or an unknown mechanism. Researchers have proposed symmetries, new fields, changes in gravity, multiverse selection, and other possibilities. None has become the accepted explanation. The fact that the observed value also permits cosmic structure makes the issue relevant to life. Galaxies are not living organisms, but they provide the environments in which generations of stars produce heavy elements and planets. A universe without large-scale structure would have difficulty developing the chain that eventually leads to chemistry and biology. The strength of this case comes from the combination of a theoretical puzzle and an observational requirement. Its weakness is that we still do not know the correct theory of vacuum energy. A future discovery could show that the small value is required by a principle we have not found. What looks tuned now may later look inevitable. The initial condition of the universe presents another strong puzzle. The early universe was extremely smooth on large scales and had very low gravitational entropy. That condition allowed structure and energy differences to develop over time. It also gave physical processes direction from past to future. Why the universe began in such an ordered state is not understood. Inflation may explain some features of the early universe, including its large-scale uniformity and the origin of density variations. Inflation itself requires an appropriate physical state, and some versions move the question rather than remove it. Again, the puzzle exists independently of life. Life uses the energy flows made possible by a low-entropy beginning, but physicists would still want to understand that beginning in a sterile universe. Fine-tuning for life and fine-tuning within theory overlap without being identical. The nuclear cases are more mixed. Carbon and oxygen production depends on properties of atomic nuclei. Altering those properties can reduce the abundance of one or both elements. Since known life relies heavily on carbon and oxygen, this sensitivity deserves attention. The strongest popular claims sometimes overstate the precision required. Stars can adjust their temperature and structure. Different stellar masses can follow different reaction paths. Useful amounts of carbon and oxygen may continue across wider ranges than a simple calculation suggests. A decrease in total abundance does not immediately mean total absence from every planet. This does not make the nuclear argument worthless. It changes the question from whether any small change destroys all carbon to how often altered physics still produces enough chemical variety for complex systems. That is harder to answer, and less suited to dramatic numbers, but it is also more scientifically honest. The same applies to stellar lifetimes. Stronger gravity or faster nuclear reactions can shorten the lives of familiar stars, but stars regulate themselves. They expand, cool, contract, and find new balances. Stable burning may remain possible across a substantial range of interaction strengths. At some point, the changes become too large. Stars fail to form, fail to ignite, or become unsuitable as long-term energy sources. The existence of a boundary is clear. The exact width of the permitted region is not. Chemistry also shows both sensitivity and flexibility. Electromagnetism, electron mass, and nuclear charge determine atomic structure and chemical bonding. Large changes could remove the rich behavior needed for complex molecules. Smaller changes might create unfamiliar chemistry that remains capable of storing information and supporting reactions. We cannot assume that life in another universe must contain our proteins, our genetic molecules, or liquid water on a rocky planet. We also cannot assume that every complicated arrangement of matter counts as life. The actual boundary between sterile chemistry and living organization remains unknown even in our own universe. This uncertainty matters because the fine-tuning argument often depends on defining a life-permitting region. If that region includes only conditions that reproduce Earth, it is too narrow. If it includes every imaginable form of organization without physical justification, it is too broad. A reasonable approach looks for general requirements. Matter must support stable but changeable structures. There must be continuing sources of usable energy. Some system must preserve information and produce imperfect copies. The environment must last long enough for complexity to develop. These requirements are wider than Earth-based biology but still restrictive. A universe filled only with rapidly decaying particles is unlikely to support observers. A universe in complete equilibrium offers no sustained energy flow. A universe that collapses almost immediately gives complex systems little time to appear. The remaining uncertainty is not whether every possible universe is equally habitable. Clearly they are not. It is whether habitable conditions occupy a surprisingly small part of the true range of physical possibilities. That phrase contains two unknowns. We do not know the true range, and we do not know the probability distribution across it. Imagine discovering that a narrow bridge crosses a large canyon. The bridge may look improbable if builders placed it randomly. It may be completely expected if the terrain forces every road through that location. It may be one bridge among millions if the landscape is filled with roads. Looking only at the bridge does not tell us which situation applies. The observed constants are like that bridge. Physics can study their structure and show what depends on them. It cannot yet show how many other bridges were possible or how the route was chosen. This is the main reason precise probability claims are unreliable. Someone may say that the chance of a life-permitting universe is 1 in an enormous number. To reach that figure, they must choose a range over which constants vary. Decide how probability is distributed, hold some values fixed, vary others, and define the conditions required for life. Change those choices, and the number changes. The result may still reveal sensitivity, but it is not an experimentally measured probability. A fair statement is that some life-relevant outcomes occupy restricted regions within particular models. That is meaningful. It tells us that stable complexity is not produced under every alteration. It does not tell us the probability that reality would select our region. Those who reject fine-tuning sometimes make the opposite mistake. They point out that probability is unknown and conclude that there is no puzzle. Yet a missing probability distribution does not make the physical sensitivity disappear. It means the interpretation must remain open. If several apparently independent quantities must fall within compatible ranges, physicists are right to search for a deeper explanation. They may discover connections that reduce the independence. They may find a selection mechanism. They may learn that the assumed ranges were physically impossible. The puzzle is a reason for investigation, not a reason for immediate certainty. This is how fine-tuning has often functioned inside physics. When a theory requires a delicate cancellation, researchers suspect that an organizing principle may be hidden. Sometimes that instinct leads to a successful discovery. Sometimes the expected new mechanism does not appear. Nature is allowed to contain values that look unnatural to us. Our preferences for elegance and simplicity have guided physics well, but they are not laws imposed on reality. A constant may be small for a reason we understand, small for a reason we do not understand, or simply small. The design interpretation faces the same need for restraint. The universe permits life, and that fact can fit the idea of intention. It does not provide a direct measurement of intention. A person may view the life-permitting structure as evidence of a creator, especially when combined with religious or philosophical beliefs. Another person may regard the same structure as evidence for a multiverse. A third may expect a unique physical theory. The scientific observations alone do not currently force one of these positions. Design also raises questions about the amount and distribution of life. The observable universe is enormous, while confirmed life has been found only on Earth. Most places are hostile to known organisms. The universe contains long periods before life was possible, and may contain a future in which usable energy becomes increasingly scarce. A design advocate can respond that the goal was not to maximize the amount of life. Perhaps the aim involved freedom, stable laws, complexity, consciousness, or purposes we cannot infer. These answers may be philosophically meaningful, but they reduce the predictive power of the claim. An unknown intention can fit almost any outcome. The multiverse interpretation offers a more physical selection mechanism. If many regions contain varied constants, then observers naturally find themselves in a rare suitable region. This could explain why the universe appears tuned without requiring the life-permitting values to be typical. The proposal becomes convincing only if the multiverse is supported by a successful theory, if the variation of constants is well defined, and if probabilities can be calculated. Those conditions have not yet been fully met. Eternal inflation and theories with many possible vacuum states provide serious reasons to study the idea. They do not yet give a complete and confirmed model. The measure problem remains unresolved. Different ways of counting can give different predictions. The nature and distribution of possible observers add further uncertainty. A multiverse should therefore not be treated as a fact simply because it offers an answer. It should also not be dismissed because other universes sound extravagant. The number of entities is less important than the explanatory and predictive success of the theory that produces them. A unique deeper law remains another possibility. Perhaps all constants will eventually follow from one structure. This would reduce or remove the question of why they have their values. We would still be left with the remarkable fact that the resulting universe permits observers, but there would be no alternate settings from which ours had to be selected. The challenge is that unification has not yet reached that point. Our best theories still require measured inputs. Attempts to combine gravity with quantum physics remain incomplete. The masses of particles and the properties of vacuum energy are not derived from a single accepted principle. It is possible that the final theory will contain one solution. It is also possible that it will contain a vast landscape. The search for necessity could lead directly back to multiplicity. Chance, necessity, selection, and design are therefore not always clean alternatives. A deeper law could define many possible states. Chance could influence which state develops in a region. Anthropic selection could determine which regions contain observers. Someone could still ask why the entire structure exists. Explanations can operate at different levels without cancelling one another. Rain follows atmospheric physics. The location of one drop includes chance. A person standing outside notices the drops that land nearby. An engineer may have designed the roof that keeps some of them away. Asking for the one true explanation of the wet pavement would miss the fact that several causes contributed. The universe may require a similar layered account. A final answer might combine fundamental law, cosmological history, probability, and observer selection. The current debate often becomes confused because participants expect one word to explain every level. There is also a possibility that the fine-tuning question will change beyond recognition. Future physics may show that space and time are not fundamental. Constants may emerge from relationships within a deeper structure. The distinction between laws and initial conditions may break down. What we call separate universes may turn out to be parts of one quantum description. In that framework, asking who adjusted the constants could be the wrong question. There may have been no independent dials and no moment when settings were chosen. The values may arise in the same way that the shape of a crystal arises from interactions among its components. This does not mean that current questions are foolish. A question can be reasonable at one stage of science and later be replaced by a better one. People once asked what substance carried the motion of a light through space. The experiments were valuable even though the assumed substance was not needed in the final theory. Fine-tuning may be pointing toward a missing mechanism. It may be showing the limitations of our probability concepts. It may be the first clue that many universes exist. It may remain a philosophical fact about one universe. We do not yet know. So is the universe truly fine-tuned? It is fine-tuned in the limited technical sense that several important outcomes depend sensitively on physical values and initial conditions. Stable nuclei, long-lived stars, cosmic structure, and rich chemistry do not occur under every possible alteration studied in our models. It is not yet proven to be fine-tuned in the stronger probabilistic sense. We cannot reliably calculate how unlikely our constants are because we do not know the full space of possibilities or the process that assigns them. It is not proven to be designed. It is not proven to be the result of a multiverse. It is not proven to be the only logically possible universe. Each remains an interpretation or research direction rather than a final result. That may feel like an unsatisfying conclusion after such a long journey. We began with the image of cosmic dials and naturally hoped to discover who turned them, what mechanism fixed them, or whether they were ever free to move. Instead, we found that even the control panel may be partly an invention of our current theories. Yet uncertainty is not emptiness. We have learned that the structure of the universe depends on connected layers of physics. Gravity gathers matter. Nuclear interactions build elements. Electromagnetism supports atoms and chemistry. Cosmic expansion shapes galaxies. Low entropy creates useful energy flows. Stars provide time and materials. Planets create local environments. Chemistry becomes capable of evolution. No single one of these facts explains life. Together they create the physical opportunity for life to appear. That opportunity is not the same as a guarantee. Most matter does not become alive. Most places are not comfortable. The universe did not rush toward observers. It spent billions of years forming stars, recycling elements, and building planets before one small world produced creatures capable of asking why any of it worked. Perhaps observers are common, and many worlds contain their own versions of this question. Perhaps we are exceptionally rare. The universe has not yet provided enough evidence to choose between those possibilities. What it has provided is a set of laws that can be understood, at least partly, by minds produced within those laws. Matter has developed the ability to investigate matter. Atoms created in stars became instruments, laboratories, books, and people listening quietly at night. That fact does not prove that the universe intended to be known. It does show that the universe is capable of producing knowledge about itself. And now you are a little farther along than when we began. The constants have not changed while you were listening, which is helpful. Gravity has remained reliable. Electromagnetism has kept your device together. The energy of empty space has continued affecting the universe without becoming urgent enough to disturb the room. Wherever you are listening from tonight, you're surrounded by the consequences of those basic physical settings. The air, the walls, your body, and the light from the screen all depend on stable atoms and long histories of stars. The ordinary objects nearby are the final results of processes that began before Earth existed. You do not need to decide tonight whether those processes reflect chance, necessity, selection, design, or something physics has not yet discovered. The honest answer is that the question remains open. It can remain open without becoming meaningless. If this journey has helped you think, relax, or move a little closer to sleep, you can like the video and subscribe to Physics with William. It helps other listeners find these quiet investigations into the questions that science has answered and the questions it is still learning how to ask. For the moment, the universe does not require a verdict from us. Its stars will continue burning, its galaxies will continue moving, and its constants will remain measured with increasing precision. Somewhere researchers will keep testing models, improving observations, and arguing politely about probability, or at least beginning politely. Here, the task is simpler. Let the unanswered parts remain unanswered for tonight. The universe may be finely balanced, naturally required, one example among countless others, or stranger than any of those options. Whatever the explanation turns out to be, the same physical history has brought you to this particular place, listening at this particular time while the larger question remains open around you. Sleep well, fellow traveller, wherever in this life-permitting universe you happen to be.